Shri Sai Ram. We will start today's program with Vedam chanting.
Om Ganeshaya Namaha Saraswatyai Namaha Shri Gurubhyo Namaha Harihi Om Yaschandasam Rishabho Vishwarupaha Chandobhyodhyamritaat Sambhabhuva Samendro Medhaya Asprinotu Amritasya devadharano bhuyasam Shariram me vicharshanam Jihva me madhumattama Karna abhyam bhuri vishruvam Brahmana koshosi medhaya pihitaha Shrutam me gopaya Medha devi jushamana na agad Vishwachi bhadrasu manasyamana Tvaya jushtanudamana duruktaan Bruhatvadema vidate suviraha Tvaya jushtarishir bhavati devi Tvaya brahma gatashri rutatvaya Tvaya jushtaschitram vindate vasusano jushasvadravino namedhe Medha ma indro dadhatu medham devi saraswati Medham me asvina vubhava dattam puskarashaja Apsarasu chaya medha gandharveshu chayanmanaha Daivim medha saraswati samam medha surabhirjushatagaswaha Amam medha surabhir vishwarupa hiranyavarna jagati jagamya Urjaswati payasa pinvamana samam medha supratika jushantam Mai medham mai prajam mai agnistejo dadatu mai medham mai prajam mai indra indriyam dadatu mai medham mai prajam mai suryo brajo dadatu Hamsa hamsaya vidmahe paramahamsaya dhimahi Tanno hamsa prachodayat Om Shanti Shanti Shanti
I would like to request the esteemed dignitaries, Professor K. Srinivasan sir, Professor Pallav Kumar Barua sir, Dr. Shailesh Srivastava sir, Dr. K. Vijay Sai sir, and Sri Rajkumar Jain sir to partake in lighting the ceremonial lamp to herald today's program. Om Shri Sai Ram. My most humble pranams at the divine lotus feet of our beloved Bhagwan Shri Sathya Sai Baba. Respected Dean of Sciences, respected Dean of Academic Affairs, respected speakers for the day, respected head of Department of Physics, respected teachers, respected research scholars, and all my dear brothers. A loving Sairam to each and every one of you here. It is my privilege to welcome you all to the second edition of Professor M.K. Sundaresan's Memorial Lecture Series. These memorial lectures are in honor of late Professor M.K. Sundaresan sir, who has been one of the architects of the department and has been a distinguished visiting faculty for over 30 years. This edition, the second edition of the Memorial Lecture Series, aimed to inspire and motivate us students to explore the various domains in photonics. To talk more on this and to set the stage for today's program, it is my honor to welcome Professor R. Gaurishankar, Dean of Academic Affairs, Department of Physics, to deliver the welcoming address. Professor R. Gaurishankar.
Om Shri Sai Ram. Offering our collective pranams at Bhagavan's lotus feet. Esteemed Professor K. Srinivasan, Professor Pallav, the Dean of Sciences, Professor Mukundarao, all my colleagues, my dear students, and all those who are watching this live through the media. A loving Sai Ram to each and every one of you. It gives me a great pleasure to stand here to welcome all of you for this second edition of Professor M.K. Sundaresan Memorial Lecture Series, which we have been organizing with the Department of Physics. Professor M.K. Sundaresan, a very renowned theoretical physicist in the University of Carleton, Canada, was a visiting faculty to Sri Sathya Sai Institute of Higher Learning for more than 2 decades. Professor Sundaresan was not only a very inspiring physicist and teacher, but as a person, with all his humility, with devotion, Professor Sundaresan used to come to Prashanta Nilayam every year in the month of around November and stay for almost a full semester till February or March, engaging himself with teaching and also sometimes with research in the Department of Physics, wherein he used to teach courses like statistical mechanics, quantum mechanics, quantum chromodynamics, particle physics, etc. And in the later part of 2008-10 onwards, he was also getting involved in teaching of research methodology for the Ph.D. students, along with another professor from the management department. And in fact, Professor Sundaresan had even compiled a nice set of notes and lecture notes for this particular research methodology program. And he was so much engaged in all these activities whenever he visited Prashantanilayam year after year. It was a great blessing for all the students at that point of time that his interaction was so fruitful for the students in terms of not only just learning physics, but more from his personality itself. We really lost him in 2017 when we got the news that he passed away, but after that his family was so very attached to the institute that they requested that the department should carry forward the legacy in terms of organizing some lectures and instituting a chair or something like that. And with that endowment, we have started this particular Professor M.K. Sundaresan Memorial Lecture Series. This year's edition of this lecture series is focused on photonics because photonics was the main thrust area of research over the last 4 decades, which was initiated by none other than Professor K. Srinivasan at that point of time in the early 80s when the university was born. And photonic research has grown tremendously in Sathya Institute of Higher Learning with a world-class facility that has come up in the Central Research Instrument Facility for laser micromachining, fiber lasers, sensing, and many other applications. So it was a very apt decision by the department that photonics being one of the primary research focus of the department, we conduct a workshop having illustrious speakers speaking to us on some of the recent trends that are catching up in the world in this area of photonics, research in photonics and optics. With this few introductory words, I once again welcome each and every one of you to this lecture series, and I pray to Bhagavan that this day we learn from these experts some of the recent happenings in this world of photonics and carry forward the research and teaching in the area of photonics. In fact, the department is envisaging to create a center of excellence in photonics in the near future, where this center of excellence will focus on research activities in photonics, optics, and lasers. With these few words, I once again welcome all of you and leave the stage to Mr. Sirshi to carry forward the events. Thank you. Jai Sai Ram.
Thank you, sir, for setting the tone for today's program. It is my honor to introduce Professor Pallav Kumar Barua, the Dean of Sciences and the President of the Institute's Innovation Council, Department of Mathematics and Computer Sciences, to deliver the inaugural address. Professor Pallav sir had obtained his Ph.D. in mathematics, specializing in differential equations and analysis from our very own institute. His research interests encompass differential equations, high-performance computing, and big data analytics, earning him the Innovation Award in 2014 by NVIDIA at HIPC Goa for his significant contributions in mathematics. Please join me in welcoming Professor Pallav Kumar Barua.
Om Sri Sai Ram. At the outset, we offer our humble pranams at Bhagavan's lotus feet. I also take this opportunity to pay my respectful homage to Professor M.K. Sundaresan. Professor Sundaresan is known to us as a visiting professor in the Department of Physics, and none other than Professor K. Srinivasan sir had invited him. We had very less interaction with Professor K. Sundaresan, but whatever we could gather about his personality is that a very astute academician and deeply rooted particle physicist, and always soft-spoken but focused in any conversation, whatever it may be. So I take this opportunity once again to say thank you to Professor M.K. Sundaresan for being with our physics department for more than 2 decades. Thank you, sir. I also fondly recollect the time we had with Professor K. Srinivasan sir while he was here leading the physics department. Personally, I had more interaction than anybody else because being in the maths department, sir had a very strong affinity towards maths, and I was also teaching some of the mathematical physics courses. But sir is known, as Professor Gauri Shankar mentioned, that he initiated the laser lab, the optics lab, what we are here after 20 years. The pioneering step, the first step was when he was leading the department. And it was, we were students that time. 2 MTech programs started. One is in applied optics, other was in computer science, and that is how, in fact, Bhagavan came and inaugurated the labs. There was a big function, and sir was very much leading the whole initiative. So thank you, sir, for what we started there. Now the department is leading. I would say this department is one of the leading departments in physics working in nonlinear optics, photonics, and these areas. And we are really happy that we have an array of experts who are going to deliberate during the day on the recent trends in photonics. If I talk about a person not standing on the shore of the ocean, but somewhere far off, and trying to describe what the ocean is, that is what I would say me and photonics. Whatever little I know about photonics and its implications, I would like to just dwell for a few minutes and leave the rest of the things to the experts to dwell upon. Recently, there are conversations in scientific circle in India that biomanufacturing is one of the areas that nations should go about. And it is a most promising thing that is to come about. And photonics has a lot to do by way of biophotonics and things like that. Being a student of computer science, we talk about data migration, data communication, and in fact, in all high performance computing work, data movement becomes the bottleneck. And it is an evergreen problem in this area. How do you solve the issue of data movement, memory management? And one of the solutions people are looking for from this area of photonics, this incoherence wavelengths and incoherence properties of the photonic structures, That should have a solution, and actually the active research is going on how that can be used for very efficient, low cost data communication and also memory management. So these are some of the areas that I know that photonics is highly promising, and next gen scientific innovations, inventions are going to happen in amalgamation, in connection with photonics. Every area in scientific exploration, be it in biosciences, understanding DNA structures or molecular dynamics, photonics has a role to play. Be it in chemical compounds, it has a role to play. Electronics and computing. So overall, if we see, is that this is one area which can contribute to many other fields and also get inspirations from other areas of scientific explorations. In short, there is ample opportunity for innovative research and inventions that can come about if we have a team of people working in a focused idea and focused directions. And that is what I think our physics department is going to go about. It is a very heartening news for us, for the university. The Department of Physics has already proposed to establish a center of excellence to pursue the scientific research and investigation in photonics and related areas. We have a strong group pursuing material sciences. That is another domain which can contribute to photonics. And also photonics can do a lot of things for designing applied, functional materials and things like that. So we are in the convergence of various groups which can really energize synergistic research that can happen. And at this juncture, without taking much time, I would request all our students that, here is a department where our faculty members, visiting faculty and their collaborators are pursuing research and innovation in directions which are going to be really trend-setting, and huge contributions for societal developments are going to come about. So it is up to the students to choose to be part of such adventures, such work, and in a way be part of some good things that is happening, novel inventions, innovations that is going to take place, and thereby choose a very good career path. And with these few words, I request all of you to take part very actively with the deliberations of the day. I am sure it will be a very successful venture. Wish you all the best. Thank you. Sai Ram.
Om Shri Sai Ram. Offering my humble pranams at Bhagwan's divine lotus feet. Respected elders, Professor Mukund Rao, Dean of Sciences, Dean of Academics, the guest speakers for today, Professor Kamaraju, Professor Saptarishi, and Dr. Manish, Professor Manish, Dr. Santosh also. Dr. Manish is not yet here. It's my proud privilege today to introduce someone to this audience who is not a new figure for SSSIHL. As Professor Pallav Kumar Barua has just told us, today's speaker for the next session who's going to chair this morning session is Professor K. Srinivasan. Let's give a big round of applause for him. Professor Srinivasan has had an illustrious career before he joined here in 1983. He finished his MSc in 1966. His Ph.D. from Annamalai University in 69. From 69 to 75, so was a professor at American College, Madurai. 75 to 77, he was with the Munich University, LMU. 77 to 79, he was with the National Research Council, NRC, Canada. And 79 to 82, he was with the University of Freiburg, Switzerland. It was in 82 that Swami decided to pull him for creating something which is now part of history. Sir was a professor here from 1983 to 2002, post which also he held many different assignments, including being a professor at S.N. Bose National Center for Basic Sciences in Kolkata. It was during his stint in NRC Canada that Professor Srinivasan came in contact with Professor M.K.S. Sundaresan. I offer my reverential gratitude to Professor Sundaresan for this day, that we are having the opportunity to get together and reminisce the good work that he did, the services that he had offered selflessly at our university. And in that connection, it was Professor Srinivasan who, I would say, found that Professor Sundaresan was one of the devotees of Bhagwan who was just here, staying anonymously, as it were. And Professor invited him to have his, he spent one full year here. And then every year he used to come almost for a semester, teaching quantum mechanics, advanced quantum mechanics, particle physics. I was then already teaching in the school, but I used to come, and it was Professor Srinivasan, who inspired us into this kind of a rigor in physics. If today SSSIHL can boast of a cutting-edge photonics lab and students all across the globe, it was because of the hard work and toil of a young professor. You cannot believe it, because when the institute started, there were hardly anybody who could teach. Swami hand-picked up Professor Srinivasan, and I think in those first 2-3 years he taught every course before he made others capable of teaching. Jain sir, who is sitting here, will vouch for me. He was one of the first batch students. Shiv Shankar Sai sir, who later on became the director of the institute. They were all his students. And for those of you who do not know, Professor Raghavendra Prasad, the current Vice Chancellor, is also Professor Srinivasan's student. Some of the things that I remember when we think of Professor Srinivasan was the rigor that he brought to physics. One of the sentences, these are things, that you cannot forget. And I quote it once in a while: physics is no nonsense. Apparently, there can be other subjects where maybe you do not need that rigor. But physics is no nonsense. You need theoretical expertise to appreciate physics. You need mathematical expertise, as Professor Pallav just now told, that he knew Professor Srinivasan because of his love for mathematics. Sir taught everything. He taught us photonics, he taught us mathematical physics, quantum mechanics, and the books that he introduced for each one of these courses, they are all all-time classics. And he used to say, just go somewhere and say that you have read from these books, and they will directly take you in. And it is true, when our students went elsewhere and said that we did quantum mechanics from Schiff, we did classical mechanics from Landau Lifshitz. It was really something very different from what was going on in the country at that time. It was Professor's futuristic vision that in the 1980s he introduced. So even though he was from a molecular spectroscopy background, but he knew that the future of physics was in photonics. And he used to often say, as the 20th century is for electronics, it is photonics which is going to be there in the 21st century. And today we see photonics everywhere. Many who do not know will not know that lasers and photonics is really spearheading so many areas of research. When you come to semiconductor and electronics, we have our own alumni now working in, for example, ASML. ASML is a topmost company in advanced semiconductor materials lithography. That is the only company in the world which does that kind of lithography, which can create those chips. You need all optical techniques for it. That the students of MSc Physics from SSSIHL is employed in ASML today is because of that futuristic vision that Professor had. You know, when ASML ships the chips, when they ship that manufacturing unit, they need I forgot the name of this of the details. You need at least 3-4 aircrafts to ship the entire equipment which is used for this kind of lithography. So if you just Google and find out where these SSSIHL students are currently, you will realize the vision. It was Bhagwan's vision that he chose Professor Srinivasan amongst so many. And it was Professor Srinivasan who thought of getting this photonics into our curriculum. And again, a very futuristic vision that in our MSc course he introduced. Along with MSc, we needed a very good background, he said, in microprocessors and electronics. And because of that, today we can boast of not just doing experiments with photonics, but we're into making some instruments. In the afternoon, we may give a brief insight into some of the research works where we need instrumentation, high-end FPGA instrumentation, software. So programming skills at that time, we had just C was coming up. It was Python, not Python, I mean, it was Pascal at that time. So programming skills, microprocessor skills, and photonics, along with all the foundations of physics, which is classical mechanics, statistical mechanics, thermodynamics, quantum mechanics, each of these. And sir has directly taught all of these courses. Today, as sir told me that he was proud and surprised to see the lab here. It is actually, when you have a baby, only the, time can tell how the baby evolves. It was sir's, hard work and toil, I will again say, because as we become teachers, we understand how difficult it is to teach one subject or two subjects. I know that sir was teaching 4 subjects, theory subjects and even more. And then setting up a lab in a village at that time, nothing was available. And today you go and see, even in 1995, 96, Swami came and inaugurated, Swami in fact gave a discourse on lasers when Professor Srinivasan brought the high power laser NDAC system at that time for almost 60 lakhs. Even now Professor Raghavendra Prasad, our Vice Chancellor, whenever we sit for meetings, he keeps telling and reminding us, look at the way that Professor taught us. What was the rigor there? You must have that. And when we were talking of purchasing some equipment, I remember just few days back, Raghavendra Prasad sir was telling us, Professor sat with the company Quanta system and then every pi was accounted for. Even today the things that we have there, you cannot dream of getting it at that price. That was the commitment for Swami's money, the commitment for Swami's time, and the time that sir spent in the university. We will all be ever grateful to Professor for all these things. And I now humbly invite and request Professor Srinivasan to give his talk and inspire all of us. Sai Ram. Was passion for teaching along with passion for English. Every class we come back and say, learn a new word. Again, something.
Om Sri Sai Ram. I don't know, I feel so tensed up in talking before you. My own children, most of you, my former collaborator and colleague, Professor Mukund Rao, and many seniors here. It's like homecoming after 20 plus years. Before I talk about Professor Sundaresan, who is one of my heroes, let me tell you a little bit about how I felt in setting up the department and how I felt when I retired from here. It was against many odds that I had to dismantle a course that was already existing to introduce a new specialization, Photonics. And people are saying it is futuristic. We have not heard of that word. Many people, many senior professors from, I don't want to mention their names, but solid support came from people like Professor Mukund Rao, Professor Sivaram from IIT Chennai and so on. But there were many people who were opposing naming a course as Photonics course in a physics curriculum. Not even in none of the engineering curriculum named that as a course, but we went ahead and named our course as Quantum Electronics and Photonics. And first 3 years we struggled to get proper equipment for that, but we equipped ourselves and our students with proper theoretical background. And as pointed out by Sailesh, we were trying to teach from classics. And it's okay. There's some sort of echo, probably. So with this background, now we try to introduce something very different from many of the universities. My motivation was that a lot of optics was done in RRI in Bangalore when C.V. Raman was there. Optics center was there in South in Bangalore, but it was forgotten. All optics gravitated towards North. Not much optics curriculum was there in the South. So I thought that we will introduce a curriculum in optics. And optics were several synonyms at that time. The new synonyms started coming, and photonics was very catchy. And as Sailesh pointed out, I used to always say that 21st century will be the century of photonics, but the century began 10 years ahead. In the 90s itself, people started using the word photonics, and so on. So in this background, and as he said, I had to jump from one course to another course, and I started learning subjects by teaching it. And most often, I used to work till late night, getting stuck up in a particular equation to open it up. I recall one particular scenario when I was teaching statistical mechanics. I got stuck up in a particular equation in an ensemble scenario. I started at 9 p.m. I struggled. It was 4:30 a.m. that I solved it. So I couldn't sleep that night. I went for Vedam chanting. We used to go for Vedam chanting round. Then came, and then that day, I remember I forgot the batch because I was thinking only that what I did. So I came and then shifted the class to the first hour and then taught that, so on. So that was the type of challenges I learned a subject by teaching it. It was the year 1985, Swami's 60th birthday. I saw Professor Sundaresan in one of the not so speakable accommodations, and I was really shocked because I knew him much earlier than that. So I took him home. We hosted him in our staff quarters, and then we recollected all of our associations. And he was saying that he was proposing to take a sabbatical soon. I said, he was preferring to go to Cambridge. I said, why don't you consider us also? Why don't you come here on a sabbatical? We will see to it that you are looked after well here. And he chose to come here. And we had a paper on energy resources. And we were the ones who to offer it for almost a decade. And maybe we should have continued it more seriously. That was on mainly on different alternate types of energy resources. Maybe had we done it, we could have really maybe pioneering in solar. If I were to repeat it, I would aggressively go about doing it, if at all. I mean, I am already 80. I don't think I will have even the remotest chance of doing it anyway. So he chose to come here. We dismantled the course. And for the first time, I took the permission from the administration in spite of the semester courses to offer a yearly course. So we offer a 1-year course in a semester scenario, and the exam was at the end of the year. And where I left, he started. We usually stop at relativistic quantum mechanics at the Schiff level, where you solve the hydrogen atom problem, etc. And then he took over from there. Oh my God! I used to sit in his class. I used to look at him like that. I wish I had learned like that when I was a student. And I sat through his course, right through the course, and then I tried to imitate it. The couple of batches later, I was such a failure myself. No, I could give only negative marks to me. He did a full course, but I wanted to do in some sort of modified version of that. He did up to QCD, and then he did quarks, special groups, Lie groups, and so on. That inspired me to introduce in mathematical physics a section on topology. I'm sure it is not there anymore. I knew that, but I don't want to look at any of what is going on. And going back a little, 20 years here, 2002, when I retired, I decided that I will hand over the department to the next chairman, head of the department. And my feeling was this, honest. This department is like my girl child. She is 20 years old, is being quote unquote married off. She is going to a different hand. I won't interfere with her life. I will bless her. And I come back today. Yesterday I saw, after 21 years, I was really moved. I looked back and then I gave 2 marks out of 100 for myself. I could give 99.9 to what you have here. I'm so proud. I'm so happy that my daughter has grown into a lady, a great lady, attracting people from all over. And we struggle the first 20 years. We taught from Marcus, we taught from optical electronics, from Yariv, sometimes cover to cover, sometimes because some of the portions are covered in quantum electronics. We try to do the end of the chapter problem and all that, struggling, bleeding way through, and finishing a class, trying to go to a lab and then try to do something, try to set up, it was a challenge. It is in this scenario Professor MKS enters. Extraordinary person. Next slide. I saw him as a very highly spiritual person. My introduction to him was, if I remember the date, on Swami's birthday in 1977. We were there in Canada. We landed in Canada on 14th November. And we were trying to settle down. I took my mother also, lugged my mother also with me. She was with me wherever I went. And a phone call comes. Somebody, I don't know how he knew my contact and so on, asking me to come and attend bhajans in their place. I didn't know what bhajan it was. And then we go there, it was Sai Bhajan. That first introduction to me to, serious introduction to Swami. And it was a beautiful day, Sai Bhajan, Swami's birthday. I didn't know much about it. I didn't know much about Sai. I had 1 or 2 occasions earlier. That's a different part of the story, not occasion to narrate it here. And from then on, almost every maybe fortnight, we used to go for bhajan in different places in Ottawa. And we got attracted towards Swami. And my tenure in NRC getting over. And then my friendship with Professor Sundaresan getting deeper and deeper. He was already chairman of the Carleton University department. And he was formerly with NRC also with the Herzberg Institute of Astrophysics. And his neighbor, Takeshi Oka, was one of the famous astrophysicists. And we got to know him. I got to know him through contacts. He was actually his physical neighbor where he lived. And our friendship grew. He used to narrate a lot of his interactions with Professor Chandrasekhar. He used to come and stay with him once. All that he used to say. And Bharati Sundaresan was an extraordinarily good host. We used to spend a lot of time. My mother used to spend a lot of time with them. My wife, they got to know Sundaresan and their family so well, so intimately. Dr. Sudhir is Sundaresan's son. Sujata, their daughter. They all became very, very close to us, very friendly to us. He was, I didn't know that he had Vedabhyasa when he was young. So he used to chat Rudram. He will sit at the back of the room and he will be chanting Rudram when bhajan was going on. And he was very unobtrusive. He will at the end of the bhajan, he will bring juice in his thing to distribute to everyone. It was such a very humbling influence on many of us. A person of that stature, a person who did his Ph.D. under Hans Bethe, a person who worked with Freeman Dyson. I mean, the names, people we hear, and then I got some opportunity to interact. But still, it was big stalwarts he worked with, and he never showed it off. And he played it very, very low key. And he will say, he will say, is it okay? Is the level okay? Am I doing it right? I mean, it was very embarrassing to me, no? He will come and say, he will do a course, high-level course, and he will do it in such a way that it is satisfactory to the current curriculum, and it is absorbed by the students appropriately. And he, as an academician, there were different facets to him. Teacher. No, I sat in his class. No, one of those old-time teachers, they will never bring notes to the class. They will keep the notes, keep it here. They won't once in a while they will consult, and they will reel out the derivations. Now, we had teachers like that when we were students, but I never could do that. But anyway, they will reel out things and very beautifully, without getting stuck up anywhere and ready for any interruptions, any questions. So he was a teacher to emulate, and without no flustering, not moving too much, and writing neatly, starting from top left and then completing at the bottom right. Anything worth writing, I always used to tell. I always found it in him. Anything worth writing, he is worth writing well. So he always did that. If it is not worth writing well, don't write it. So just talk about it. So he always practiced that. The second quantization equations, QCD equations, the fermion quantization, everything he will write so meticulously. No mistakes, no subscript will go, no superscript will be missed. Proper superscript. A dagger is in the correct place, a subscript in the correct place. Meticulousness. You have to, I mean, most of you must have seen it, but I sat through his class. On top of what I was doing, I completely sat through all his classes, all his lectures, entire lecture, and it was a treat. And as an advisor, I took a lot of advice from him, some of which I cannot share. We used to discuss about so many things, the environment and the scenario, and he was such a perceptive listener and a very careful advisor. He will advise in such a way that he is not advising, but you just pick it up. Oh yeah, this is it. I missed it. He got it. No, that type of, it's very rare. That ability to give an advice without being perceived as an, no one like to be advised. No, advice is only given. It is never taken. Just this is my belief. You can give n number of advice. You can keep giving. Never listen. They will do what they want to do. I've seen in my little 40 plus years of teaching, I've given n number of advice. It has never followed. It will be assimilated and then followed in its own style. And his style of advising, I think it is a typical German style. So he was trained by Hans Bethe. Hans Bethe was trained in University of Munich under Arnold Sommerfeld. That's where I worked, not with him. And Arnold Sommerfeld was followed by Stern Gerlach. And my professor whom I worked with, Raman spectroscopy there, was Gerlach's student. So that tradition, Sommerfeld, Gerlach, that type of tradition. And Bethe was one of Arnold Sommerfeld's students. Arnold Sommerfeld is known to be a very rigorous teacher. So the typical German tradition, and also some of the, I don't know if they follow it, in the 70s, if you enter a department, there will be a genealogy board. The present professor's name will be down, and then they will trace at least one Nobel laureate on top. So Nobel laureate, then they will put the arrows, and then the present professor. So I used to claim like that, no? Anyway, the tree goes to Sommerfeld. I'm nowhere near anyone of those. Hans Bethe, in his later years, he was living in Cornell, and my daughter lives in Cornell, so I had a glimpse of him from a distance once. So he was too senile, he was too old, but the formidable Hans Bethe, we must have heard about him, Bethe's Hall-Filter formula, Bethe's books, and he's trained under him, and he's advising. It seems that is the style of the German. I told you, the advice from the German professors will be like that. The typical, the American way of saying also, no, if I were you, I will do this. If I were you, I will do this. That type of advice, not talking down type of advice. That's a typical Germanistic thing adopted into American style. As a researcher, I have a lot of admiration for him. He inherited the Bethean culture originating from Sommerfeld. If you ever happen to read about Sommerfeld, you will get a glimpse of his style. His style always percolated to others. And among few things, the Greiner series of books now, almost all subjects. Before that, there was a Sommerfeld series of books. Please, they are available in the net. He has written on all topics, Sommerfeld series of books. Before that, Planck wrote, but that was never, I don't think it was translated into English. So Planckian series, Sommerfeld series of lectures, and the Greiner series is the latest. So the Germanistic influence was there, I perceived in Professor Sundaresan. I think almost that's the end of what I wanted to talk. At that time, you have some walk through memory lane. Professor Sampath was the Vice Chancellor, and he had such a admiration for people like Professor Sampath, who were ready to give, not take anything. So he was a giver. So we used to have wonderful time, Professor Sampath as the Vice Chancellor, and Professor Sundaresan, Professor G. Venkatraman, and myself. All four. Others were Vice Chancellors. I have the age to mention their names. And we used to sit and talk about wide range of subjects on top of the type of work I have to do. They won't let me go, so I have to sit and I always benefited with conversation like that. Every conversation made you richer. In every conversation you learned something new, a new point of view, a new vignette view. Amazing. And another characteristic which I could never learn in my life at all, he never will lose his cool. The worst of scenario, he will never lose his cool. The easiest of thing, I lose my cool. I don't know. Still, I get scolding from my daughters, from my grandson now. So that is another trait. Extraordinary level of cool-headedness. Absolutely cool. You can't excite him. You try to say something to provoke him. And there was a board of studies meeting. Those days it's a different story. You do everything and then the board of studies member will come there. They won't have time to go through any of these. They will sign and go. So you have to do everything you have to do. And then my critiques were on one of the meetings. I talked to Professor Sundaresan was there as a member of the meeting, and Professor Venkatraman was another member of the meeting, G. Venkatraman, former Vice Chancellor. No, they were all with me on the same wavelength. They used to say, oh, you're teaching from Landau Lipschitz, teaching from this team. Oh, this is wonderful, wonderful, and all that. The meeting came. That day I was running some temperature. I was because I had to work till late night. I didn't have a secretary. I had to type the whole thing myself. And my multiple copies and things like that. Suddenly, they team up. JGV and MKS team up. And then saying, why are you putting so much of maths? I have quite motivated them. I told them what my thinking about this is. And then they started they dressed me down completely. I said so many things. No, I just simply walked out. You just do whatever you want, sign it, send to the present Vice Chancellor. I just walked out. I couldn't take it because so much effort is I talked to the, I gave my approach to why I put something like this. Everything single-handedly one had to do. My approach was, I was trying to use optics as a paradigm to learn physics. Optics as a paradigm to learn physics. Optics, photonics is the special subject, that's the goal. But to go there, you learn entire physics through, as you go through. How do you do that? It's a challenge. Because all the structures that are there in physics is in optics. Every mathematics, you tell me a mathematical structure, already it is there in optics. So, learn that mathematics as you go through playfully. When you go to optics, it just follows through. You don't have to go behind the mathematics. Mathematics will come behind you. That's the idea we had. So, we always thought the trio of theory, experimentation, and the much talked about simulation. These three should be part of the paradigm in learning. At the same time, you should use optics as a paradigm to learn entire physics. That's the idea with which we proposed photonics. Later on, if somebody wants to put some other specialization, say particle physics, they should use particle physics as a paradigm to learn physics. That was my idea. I left it at that. I didn't use this word at all at that time. Later on, when I went to SN Bose and so on, I was invited to many places to, why you did this? Why so much of mathematics? Why you have topology in your math physics course? For some of you, if you are interested in listening to the name of a author, Nakahara is a name of a book, Nakahara. It is available in the net. We taught a sizable portion from there. Professor Jagan Mohan Rao from Maths Department used to teach for 2 years, and then he said, I don't have time. Then afterwards, I took over. I tried to learn and teach. And if you look back, that's what it is. That is what is needed in many areas of advanced physics. If you want to talk about Lie groups, you have to go through the geometry of it. And why do you need it? Yeah, you pick it up. Do your specialization. But pick up all this know-how. It may be useful. For example, there is a branch called Lie optics. And if you know Lie algebra and Lie group, you can do Lie optics, vision. Our vision, it seems, is a Lie process. Google it and find out what Lie process has to do with vision. Why I am saying this is, all this inspiration, it was there. And suddenly, probably to just just to strengthen my argument, probably they said, why are you doing it? But I just lost my cool. I had to leave that. So looking back, I feel very bad about it. This is just to say that how cool he was. Under any circumstance, he was very cool. He never loses his cool. That one characteristic stands apart. Absolutely stands apart. I think I've talked too much. This is an occasion to talk about photonics. I'm out of photonics for the past 23 years. Had it been 23 years back, I would have talked about photonics and my passion about that. I was fascinated by phase conjugation at that time. I was fascinated by Raman-induced Kerr effect at that time. I was in the midst of it. I was in Jean Tarrant's lab in France when cars was invented. I had an opportunity to interact with Adalbert Owen, who was in the Sandia National Laboratory in the West Coast. I was in correspondence when coherent gain spectroscopy was coming in a big way. As a spectroscopist, I began as a spectroscopist. Raman spectroscopy was something extraordinarily special. It won several times over Nobel Prize. You look back and then see you can discover. And it is one branch of physics which has 5 renaissances. Google and find out. 5 times over. Sunlight was used as to win the Nobel Prize. Right. Then start from there. 5 times over Renaissance. Only one branch, as far as I know, one branch of physics. And I worked with the very in the 60s, 1960s, lasers were yet to be brought into India. So we had mercury excitation, photographic plate, and so on and so forth. Anyway, so I went through this, and the exposure to Professor Sundaresan, to me personally, to my family, and to our department here is something Swami's gift. With that, I would like to thank you all for your patience. Thank you. If you have any comments or questions, I can take one or two. If no comments, thank you.
Thank you so much, sir, for sharing your memories with M.K. Sundaresan, sir, and sharing your experiences of the department in its inchoate stages and how you had contributed to the department adopting the specialization in photonics and that coming into fruition right now. So I'd like to request Mukunda Rao, sir, to felicitate Professor K. Srinivasan, sir, to provide Professor K. Srinivasan, sir, with a token of gratitude. We will now break for a small 10-minute tea break. Sairam. The first speaker for today's morning session of this memorial lecture series is Dr. Saptarishi Chaudhary. He's an accomplished physicist with a remarkable academic and research background. Dr. Chaudhary had obtained his Ph.D. in physics from the Tata Institute for Fundamental Research, focusing on the Bose-Einstein condensation of rubidium atoms in an infrared optical dipole trap. Currently, he's serving as the Associate Professor at the Raman Research Institute, Bangalore, and he heads the QMix lab at RRI, which focuses on ultra-cold quantum gases and disordered potentials. Throughout his career, Dr. Chaudhary has held prestigious positions globally, including postdoctoral research roles at institutions such as the Center for Quantum Technologies at National University of Singapore and the European Laboratory for Nonlinear Spectroscopy at the University of Florence in Italy. He has been recognized with various fellowships, awards, and research grants for his outstanding contributions to the field of physics. With over 30 peer-reviewed publications in reputed journals and numerous invited lectures at conferences, Dr. Chaudhary's expertise and dedication to advancing scientific knowledge are truly commendable. His supervision of graduate students and teaching activities further exemplify his commitment to nurturing the next generation of physicists. Dr. Chaudhary's significant contributions to the field of physics and his dedication to research and education make him a valuable asset to the scientific community. It is truly an honor to have you, sir, here with us delivering a talk. Sir will be delivering a talk on the topic ultra-cold neutral atoms as quantum devices. Without further ado, please join me in welcoming Dr. Saptarishi Chaudhary.
Thank you very much for this kind introduction, and I am truly humbled to be here. It's really wonderful that you have given this honor for presenting this lecture here today. So I worked in the interface between photons and atoms. Our group is known as Light and Matter Physics Group. So I will be speaking mostly from the side of matter, how matter interacts with light and how we can use it for some modern day technology development. So that's why I have given the title Quantum Devices. So please interrupt me during the talk. So the talk is prepared in such a way I will give a more general introduction to the field, so that I was told that it should be made keeping in mind undergraduate and postgraduate students. So experts, please interrupt me also if you think that some of the basic concepts I am taking a lot of time to explain. But then, I will try to give a few glimpses of what we do in our laboratory and what we plan to do in near future. So, for example, these are a few. Do we have a pointer? That will. Huh? Oh, okay. So I can try to make. Yeah, I can do that. Yeah. That's good. So throughout the talk, I will try to present a lot of, no, it's okay. Probably this pointer is visible, right? I will try to present a lot of pictures from the laboratories, and I will purposefully avoid a lot of mathematical details. But if you have questions, please ask me. So these are some of the things what we do. We look at quantum processors using these mixtures of cold sodium and potassium atoms trapped inside our ultra-high vacuum chamber. I'll explain what I mean. Then, if time permits, I will explain some new direction of spectroscopy, which is known as spin noise spectroscopy, and how we employ it for the purpose of magnetometry. That is very, very precise determination of the magnetic field, and its applications will be clear. So, we also trap these cold atoms in structured potentials and then look at what is known as many body physics, which has some connections with material physics, and we take a bottom up approach. So, and then we do also study about quantum diffusion and impurity problem and quantum optics with neutral atoms. Today I will not be talking about the last two topics. So, I would like to introduce my team. So, these are the present PhD students, and Maheshwar and Shagar, they have completed their PhD in the last 2 years. They have left for their postdoctoral research. And then we have theory collaborations with Professor Dibyendu Roy and Supurna Sinha and many others. Dibyendu and Supurna are in RRI. And also we have experiment collaboration with Professor Dr. Sanjukta Roy. And then we are funded by these institutions. Okay, so since I will not be going into too much details today, so some of the relevant publications are listed here. I assume this talk will be recorded, so if you want to go into the details of the work and want to contact me, I'll be very happy later on to do that. So these are some of the work what we do and publish recently. Okay, so let's get on with the talk. So, just before starting, this year was important. Year means 2023. That was 75th years of Raman Research Institute, and we paid homage by creating this holographic projection of Raman's bust and Raman's this particular logo. And I will tell you that using this kind of holographic projections, we can also trap atoms in space. So, some examples I will give at the end. We create this kind of holographic projections of light using this kind of devices which are known as MEMS, digital mirror devices. Okay. All right. So, what are the context and motivation of this kind of work, what I am going to explain. For example, ultra-cold atoms have been used over the past 2 decades for studying many pioneering physics investigation. I will list some of them. For example, superfluid to Mott insulated transitions, BEC BCS crossover, and then even controlling the 2D material, how they behave, and some of these things you would have encountered like BKT transitions and Anderson localization and glassy transitions, etc., and vortices in quantized media. So, the reason why I am telling this is because most of the manifestation of this kind of physics are envisaged in condensed matter system, but condensed matter system being wonderful systems which are of everyday use, they pose significant challenges because the systems are marred by so-called disordered and interactions which are not always controllable. In case of cold atoms trapped in space, we have a huge amount of controllability over the system parameters, which helps us to understand this kind of physics like quantum phase transitions and the vortices in quantum material in a much more coherent fashion. And that is why this kind of physics have been at the forefront once the cold atom system have come into focus. I will explain how these cold atom systems are prepared in the lab, because that's what we do on a daily basis. So, moreover, since I am also going to tell you something about what we do with mixtures of cold atom, because the single particle physics, one thing I wanted to highlight, that all these are manifestations of electrons in the condensed matter system, and the role of the electrons are now played by the atoms which we trap and cool. And moreover, we can control the spin of the electron, quote unquote, in atoms, because we can have both fermionic and bosonic atoms, whereas electrons only come in the fermionic form. So that is why the systems becomes rich. Now, in a typical condensed matter system, there are only one type of particle, let's say electrons, which are moving around. There are of course phonons, which are the lattice vibrations, which are bosons. But then this electron-phonon interaction is something which is of fundamental interest to know about materials much more. So these cannot be studied very well for most of the experiments one can think of in condensed matter. So some of these studies can be simulated in the particular examples what I will be giving. One such example is that you can have these bosons which are in a bath of fermions. Imagine that a sea of electrons and then a few bosons which are imprinted in that, or the vice versa, where the electrons, a spin up and spin down electron are separated, but then a bosonic bath is connecting them. So this kind of systems we know as boson-mediated fermionic interaction or Fermi-mediated bosonic interaction. The reason why I am talking about these things is that knowing about dipolar interactions or this kind of mediated interaction gives insights about high TC superconductors, which are something which is kind of a holy grail in present day understanding of physics. So having said that, there are not just these. So I talked about quantum simulation of complex condensed matter system, and not only that, also the soft matter and solid state system can be simulated, which is all part of this quantum technologies using ultra cold atoms and ions, whereas you can also use them for quantum sensing and metrology. One example I'll try to give towards the end of the talk, how we can measure magnetic fields to a precision which is far exceeding the magnetic field generated by your brain waves, for example, without attaching anything or putting your brain inside any machine. So that kind of sensitivity we are talking about. Of course, these atoms can be used as what is known as qubits or quantum bits for quantum computation. And also, you know, there are recent proposals of looking at ultra-fast quantum dynamics using these trapped atoms, and they can also be used as dipole antennas. Okay, so let me give you about, I have been talking about ultra cold. So you can look at this scale, and typically we work at this region, which is after so-called laser cooling, which I will explain, something called evaporative cooling, and then quantum degeneracy. And the typical scales are of the order of nano Kelvin. And there is a way to describe that. In the dream sequences in movies, you see those nitrogen, liquid nitrogen kind of things. So they are very hot compared to this. They are like, you know, million times hotter than these atoms what I will be talking about today. So this is one aspect. So, and this is very, very near to absolute zero. And in a lot of times, this is also known as coldest matter in the universe, because as you know that even the cosmic microwave background radiation is much, much hotter compared to the temperature scales what I am talking about. So I'll explain what I'll. Okay, so there is a list of things which attracts many of us. For example, the wave nature of matter is most relevant at this temperature, and then quantum statistics, for example, Bose-Einstein statistics and Fermi-Dirac statistics is what plays the most interesting role. For us, the another interesting thing is that these atoms are moving very, very slowly. So the textbook problems of looking at an atom, studying its property can be handled in this experiment. Most of the other experiments actually shows a version of what is typically taught in textbook, but the experiment what we do in an ultra cold atom lab is actually what is talked about in textbook when we say about spectroscopy, etc. Then these are inherently microscopic. We are talking about atom by atom interactions, and also thermal fluctuations are negligible, so noise in experimental results are extremely low, and so some of the other things what I had already explained. Okay, so let's get into this physics of quantum gases. So imagine that there is an external potential, and most of our laboratories deals with external potentials which are harmonic in nature, and towards the bottom of the potential the energy levels are separated in the way all quantum mechanics textbooks describe. And then if these atoms are bosonic, that means they have integer spins, they can all condense into the lowest possible ground state, and this is known as the Bose-Einstein condensate. When all the atoms occupy the same state, and since they are bosons, they can do that. There is no restriction. On the other hand, if they are fermions, there will be, one atom each lattice or each energy state, and they will fill up to what is known as Fermi energy. And most of the experiments will revolve around these concepts. So let's stick to the Bose-Einstein condensation. The theoretical description has been given by S.N. Bose, which Einstein later integrated into the matter, and then the first prediction came around 1924, but the first demonstration of Bose-Einstein condensate came around another 70 years later, and there was some technological challenges which needed to be answered, and this is what I will be talking about today. Though there was some indication of superfluid helium, and even superconductivity was understood to be the condensation of the Cooper pair, but the real demonstration of Bose-Einstein condensation, which was only in 1995. So what happens here? So most of the thermal physics can be explained by this billiard ball model, whereas as you start to go into lower and lower temperature, the corresponding de Broglie waves associated with each individual atoms becomes important, and then closer to T equal to 0, or the kind of temperature we are talking about, nanokelvins, the nearby de Broglie waves overlap if they are bosons, and then this overlapped giant matter wave is known as the Bose-Einstein condensate, and you can see it. Means that is the incredible things. For example, when I am here, one thing what reminds me of magic, the magic from the perspective of spirituality. But in the lab, when, for example, you observe a giant matter wave of millions and millions of atoms, and which you can see on your camera, so that's nothing short of magic. So that's keeps me motivated. So it definitely took 70 years to observe the first BEC. There are several Nobel Prizes, several sets of them awarded for realizing many sub-steps. I will try to explain a few of them. And then going beyond the philosophical implications, etc., we will focus today on the technological applications and so on. So requirement, as I said, is that so-called phase space density needs to be larger than some number of the order of 1. And so if you calculate some back of the envelope calculation, that requirement says that with a reasonable atom number density of 10 to the power 14 atoms per centimeter cube, if you increase the density much more, then they will condense into some non-interesting phases like liquids or solids, which you don't want to study so much. So you need to keep them dilute enough, but you still need to have the phase space density high enough, so then the temperature needs to be pretty low. So this step is achieved by various sub-steps. So one of the important substeps, what is known as laser cooling and magneto-optical trapping. So I will explain in 2-3 slides, and then I will also try to explain some of the other steps what we do in the lab. So that is called trapping these atoms in what is called optical tweezers and magnetic trap, and then evaporative cooling. Okay, so what is this step of laser cooling? So that is where the atom-photon interaction manifests with its true glory, I would say. So this takes down from room temperature, or it can be even higher temperature, cloud or clusters of atoms to something already of the order of microkelvin or sub-microkelvin in a single step. So something which is familiar to all of us is the radiation pressure on comets. So that have been studied actually long time in the past. So there is one auxiliary comet tail which can be explained only by the radiation pressure of the sun when the comet comes very close to the sun, and that is because of the solar photons which imparts momentum onto the particles carried into the comet, and that is significantly serious, and that is beyond the standard explanation of other definitions of comet tail. Now something similar is used for the laser cooling. Imagine an atom which has only 2 levels, which is a simplified picture, but it works to some extent. So in that case, if the laser light frequency is scanned across the atomic resonance, there is a sharp resonant absorption. So this is a resonance absorption, and this is pretty sharp. Now imagine the atom is fixed in space, and if you shine the laser light onto that atom which is isolated and fixed in space, then apart from getting into the excited state, the atom will also absorb a momentum kick, h bar k, divided by the mass of the atom, so that will be a velocity gain. So a zero velocity atom starts to move. Now imagine the other way, the atom is moving towards the laser, and the laser frequency is fixed in such a way that in atom's rest frame, it sees the laser on resonant. So then also the atom will absorb a photon, and it will also absorb a momentum keying exactly opposite to the direction of the motion of the atom. That step is clear, and then this mass of atom being very low, and h bar k, k is 2 pi by lambda of laser, right? You can calculate this velocity change can be significant, and it can be so large that a single photon collision will slow down the atom at a very significant level. And imagine that there are multiple photons we can control to impart the momentum exactly how much is needed to slow down an atom which is moving with a velocity of around 300 meter per second, which is the most probable velocity in the room, right? You know, from Maxwellian velocity distribution. So now, so this is how you can actually create so-called Doppler kick, and this is why this is known as a Doppler cooling mechanism. So the picture is that an atom moves towards the laser, it gets excited, and then it gets a momentum kick, and then afterwards the atom needs to come down to the ground state, and this ground state photon can be scattered in any random direction. So averaged over a few photon scattering, this excitation de-excitation phenomena will only create a directional kick. So you can slow down the atomic jet in one particular direction. So this is how the Doppler cooling actually works. So on an average, the atom is slowed down, and this is a strong interplay between the internal and external degrees of freedom, leading to slowing down or cooling, because for us the temperature is the kinetic temperature for atom. Now imagine that you have assigned laser beam from both left and right direction. So there will be a slowing down force from the left and from the right, and then you can add these two forces, and you can see near the center of these two overlapping laser beam there is a linear force, and so this force is proportional to the velocity, and this is very familiar to a viscous drag. So this is also known as optical molasses, like the standard molasses where you have things slowing down once you drop these, and this can be actually generalized to 3D, and there are some details which I will not go. The light needs to be correctly polarized to talk to different atoms with different magnetic state, and you can actually create blob of or a cloud of atoms which are very, very slow. And these atoms are just slow and staying there inside a vacuum chamber. Why vacuum chamber? You don't want any hot atom to kick them to throw them out of the trap. So that's the issue. So now in order to trap them, you use another concept which was talked about just previously about Stern-Gerlach experiment. You know that fantastic concept of Stern-Gerlach experiment, and then there is also a deflection when magnetic particles moves. Atoms are also the tiniest magnets possible, and then somehow this excited state is energy is proportional to the distance if there is a magnetic field created in the lab which is also position dependent. And by borrowing concept from the Zeeman effect, Stern-Gerlach concept of projection of spins in different directions and so on, we can actually now construct a situation where laser cooling and the magnetic field dependent force can be added together to give a trapping which is a position dependent trapping, which is very similar to the restoring force. And two together, there is an optical part and magnetic part, so we call it magneto-optical trap. And then using this so-called inhomogeneous magnetic field in space and laser light coming from 6 direction, plus x minus x, plus y minus y, and plus z minus z, you can actually now trap a huge number of atoms. So this white region is actually the fluorescence emitting from the atom in my lab, and then you can actually collect into a camera to know where these atoms are trapped, how many photons are emitted per second, you count them, you know how many atoms you have trapped, and I will tell a little more about this. Okay. Some numbers you can look at. Typically at room temperature, this is like 30,000 centimeter per second, and these atoms are moving so fast, any measurement of meaning is becoming difficult, but here they are like moving even slower than I can move across the stage. All right, so okay, so this is another picture of potassium atoms. This was rubidium atoms. Anyway, don't go by the color because these pictures are taken by standard mobile phone because we have pretty large number of trapped and cooled, so you can see them. Many of you, I think, have visited the lab and you have probably seen them trapped, and so you can do some magic, like, you know, take a magnet near and these atoms move, and so it's interesting. Anyway, so for development of the methods of cool and trap atoms with laser light, 1997 Nobel Prize was awarded to Steve Chu, Claude Cohen-Tannoy, and William Phillips. So of course the theories were harder than I tried to say, but anyway, so this is the basic concept. So then, is it enough to be using them as quantum devices? Yes, for many application you can do a large number of demonstration of quantum advantage using these cold atoms, and many people do that nowadays. But we are interested to go one step ahead, going from this micro Kelvin to so-called nano Kelvin. So we hit a limitation. The limitation is called a single photon recoil. The same thing what I told you about the excitation to de-excitation, the spontaneous emission, so that gives a small jitter, and that jitter itself can be jitter in position, that means in velocity, can be calculated to be a temperature which is already higher than the so-called many-body critical temperature. And in order to avoid it, so what we do is that we can transfer these atoms into what is known as dark trap, and dark trap can be using magnetic or optical traps. And so one of the concept is again was awarded with Nobel Prize recently, I think in 2018, to Arthur Ashkin, that is to create trap for particles using focused light. And he of course developed it for not just atoms but also for many particles including biological system. So the concept is similar. You focus a light very tightly, and then there is something called light shift, or in advanced quantum mechanics the corresponding AC Stark shift, and that AC Stark shift actually causes the ground state energy to become position dependent, and so that is a potential energy structure in space if you focus very, very tightly such laser light, and then the atoms which are already pre-cooled, they go and get trapped inside this kind of optical dipole trap or tweezer trap, right? So they are called tweezer for a reason. So they can be used as a tweezer for the traps. And similarly, just by magnetic field creating what is known as anti-Helmholtz configuration, you can create a zero at the center, and the magnetic field will be increasing away from the center, and the atoms can be correctly spin polarized to a particular magnetic state to be attracted towards the zero of the trap, and that way also you can trap these atoms. Of course, you cannot do this from room temperature, because in order to trap atoms having that much energy, you require an enormous size, but already pre-cooled atom like what I have shown can be transferred easily into such traps. And once you do that, for example, the principle of this magnetic trap is something very similar to a toy which I am sure many of you have seen. This is known as Levitron. So that is, you take a magnet and you take a spinning object, and this object keeps on rotating near that magnet. It's kind of trapped. So it's a classical interpretation of so-called magnetic trap. And you can make it, it's not so difficult to make actually. So now these atoms are now trapped in such harmonic potential, either magnetic trap or optical trap, and then your job is to selectively kick out the hotter among them. So you have to somehow select them, and then the ones which are remaining, they will interact with each other, and they all will go down to the absolute ground state of the trap. And this is very similar to what is known as evaporative cooling. So you just have to blow out the hotter of them. So there are two ways to do that. If these are magnetic state, you just flip the spins of the magnetically particular atom with a energy, and this is done by what is known as a radio frequency radiation, which is very narrow, so you can actually address particular energy levels. And in optical traps, one is what we use is you reduce the depth of the trap by reducing the intensity of the trapping light. So by doing that, you can get all the atoms in the same phase, and as you can see, this was one artist impression of what this Bose-Einstein condensate is, and then the Nobel Prize was awarded for first achievement of Bose-Einstein condensate in 2001 to Wolfgang Ketterle, Eric Cornell, and Carl Weyman. Alright, so I show you one picture from one of my very old labs where we had created a Bose-Einstein condensate of rubidium atoms in space. These are absorption images of these million atoms, and then this kind of systems are used for various. Okay, so so this is sometimes back, around a couple of decades back. So what are the modern experiment one do with ultra cold atoms? So we do with mixtures of two BECs, then use the BEC as quantum resources and use that for further investigation and technology development. So this is a bird's eye view of the experiment what we have. We have source of ultra cold atomic jet here. So the experiment starts with potassium atomic jet in the left side of the experiment here and sodium, and then both of them are trapped together through a small differential pumping hole into the main vacuum chamber. By the way, inside the vacuum is always maintained something like 15 orders of magnitude below the atmospheric pressure, because we don't want even a single hot atoms to be around to knock out a cold atom. So that is a technological challenge. To get that, we have numerous ion pumps, sublimation pumps, turbo pumps, etc. So, but then in here, the mixture of these cold atomic clouds are captured, and presently what we are doing, we are transporting these atoms through this small tube into another region which is 60 centimeter, half a meter away from the main trap, because here the entire vacuum system is made out of glass, and so we have a much better interrogation region to see this atom light interaction. and the transport is done by what is known as magnetic conveyor belt. So the atoms are trapped in a magnetic trap and the entire trap is moved, but we don't move it physically. What we do is that we have various coils which are overlapping with each other. We transfer current from one coil to another in an analog way, so that the zero of the trap moves and the atoms just follow. So most like, okay. So then the jet of atoms are created inside this vacuum chamber. I explained roughly how this laser cooling and trapping works without getting into too much detail. So if you come to the lab, this is a few months old photo, is that all the lasers are actually frequency stabilized, high resolution spectroscopy are performed to what is known as laser locking, and polarization and phase stabilizations are done using devices called acousto-optic modulation and electro-optic modulator and different phase plates like wave plates, etc. And entire thing is done in one optical table. And then the light is transported using the polarization maintaining single mode fiber. By the way, I should mention the frequency stabilization of laser is 1 part in 10 to the power 10 typically, or better. That is required, otherwise instead of cooling the atoms you may end up heating the atom. So this needs to be much lower than the resonance line width of the atom. And then the light is transported using the fibers, and then the optical alignment for trapping and cooling somewhere inside here. And then as you can see from one part of the vacuum chamber, you can see a nice sodium magneto-optically trapped atom and potassium magneto-optically trapped atoms, and we characterize how fast we can load, etc. Okay, so how do we know the temperature? So again, the simple principle is what is known as absorption imaging. We shine a resonant light onto these atoms, and these atoms cast a shadow, and we image the shadow. It's easier said than done. Actually, there are typically many lenses which make sure that we get a diffraction-free imaging onto the CCD camera, and then the dark region is where the atoms have cast a shadow, and from that shadow we can measure various things. For example, the darkness of the shadow, the total counts in the CCD pixel already tells you the number of atoms, which you know the parameters for interaction between atom and light. And then the temperature estimate is done by allowing these atoms to expand and fall under gravity. As they expand and fall under gravity, their size grows, and the kBT is proportional to the rate at which the size grows. So it's very simple, and that's how we actually measure the temperature. Of course, we get limited by signal to noise ratio. Such images are typically marred by a lot of interference and diffraction patterns, because we are talking about all single frequency polarization stabilized light. Yeah. Okay, when you are imaging, yes, that's a good question. So the imaging is done for an extremely short time. So we typically make sure that the flash of light lasts for only a few microseconds. So whatever momentum is imparted onto the atom during imaging, that is negligibly small, and that's also corrected. So typically how the images are taken is that we take a dark frame, we take a bright frame, and we know that what would have been the momentum imparted to the atoms by the photons which we are doing. So we also subtract that out. So yeah, good question, but
supersonic jet spectroscopy. So there also you go to ultra low temperatures. Means like
transverse.
Yeah.
So when we say supersonic jet spectroscopy, the ultra low temperature is only in the transverse direction. Here I am talking about the entire cloud, means means you are not taking a spectroscopy from the perpendicular direction. So whichever direction you take this image, it will be the same. Yeah. And also, you know, when you have the supersonic spectroscopy, in a way that in the frame of moving two atoms or molecules, they are cold with each other, but in the so-called absolute frame, not. So we are more interested about the quantum many-body overlaps. So
So there you're converting your rotational and vibrational degrees of freedom to
yes,
translation.
yes, yeah, sure. Okay, so one of the thing is that these images are marred by a lot of diffraction and interference effect. So we have a technique in the lab developed recently to use an artificial intelligent algorithm which we developed recently to clean up those interference pattern. So I will not get into too much details of that. So the idea is that using that we can even detect with a sensitivity of few tenths of atoms. So that means you can measure a million atom with a signal to noise ratio of a 10 atom fluctuating in number. Well, means 10 is too much, maybe 100. Yeah, means. All right, so okay, so this is how we enhance the signal to noise ratio of these images. You can see once we process the images using this algorithm, these are atoms, the bright yellow. So you can clearly see that how nicely. Okay, so another thing what we study, how much time do I have? 15 minutes? Okay, I will continue, sorry. So we also study what is this atom-atom interaction. The typical way these atoms interact with each other is via exchanging a photon. So one picture is that if an atom goes to the excited state, it becomes a dipole for a short time because the ground state is an S state or L equal to 0 state, angular momentum 0. If it gains an angular momentum, then the L equal to 1 state. So this is a dipole, and a dipole will always try to induce a dipole which are nearby. Since we have these mixtures of atoms, so there is a dipole induced dipole interaction, and that interaction, if the dipoles are side by side, this will repel, and if the dipoles are head to tail, they will attract. Either way, this additional interaction causes a huge force in which these atoms are trying to fall into each other or going away, and that causes a significant loss of the atoms from the trap. And this loss also, if we experimentally measure, for example, these are experimental data points in the lab, is a measure of the nature of that interaction, which is nice because at an atom by atom level, studying the dipolar interaction or the interaction between atom is something of fundamental interest. So we have done quite a lot of this kind of interaction study, changing what is known as impurity fraction. That means one atom is an impurity, and in our case these are all engineered. For example, I can put how many impurities I want to put, and then I can also look at the interaction as a function of quantum state preparation. I can prepare these atoms in any of the possible energy states, magnetic states, and depending on different states I can actually make this interaction stronger or weaker. So something which I will not talk about, recently we have seen, this is one publication we are trying to finish, is that this interaction also qualitatively changes the dynamics of these atoms. How these atoms are moving inside the trap, that can also be controlled, and that has a, yeah. What is selectively exciting one of them? Yeah, so for example, we can shine laser only a particular region of the trap. So you have seen that there is a large trap, so we can focus the laser to selectively excite a few atoms. Well, means if you ask me saying that I want one particular atom, this is one research activity in our lab, we are going for that, but out of a million, if you say that I am selecting 100, so that is already like a impure. So we do something more. We also selectively put it in a particular quantum state. For example, there are various states which are available. So we do selective excitation, de-excitation using 2 photons, and then actually we can also not only select an atom but also select the state of the atom. And then okay, so some of the other things what we are doing now is that we use this fantastic device which is known as the MEMS device or digital mirror device. We can create, this is nothing but 1000 by 1000 micromirrors. So nowadays you can buy these micro electromechanical devices. So we bought one, and then we can program it to have any shape you want, and then you can do what is called a one-to-one image of light falling on such a mirror device, and then you can create quite exciting intensity patterns in the space. Moreover, we can also make this pattern change in time with one structure to another structure with a time delay as low as 93 microseconds, almost the same kind of time delay, or even slower, even faster than the coherence time in the atoms. We can make sure these cold atoms can maintain their state coherence of the order of a millisecond. So let's say that is like 1000 years, and then we can actually change the state of the light which is interacting with them of the order of something like 100 microsecond. So that means at a time scale faster than the atoms decohere, we can actually manipulate them. And for example, this is one example where we can create this kind of array traps. So for example, here we created two focus next to each other, and then a bunch of around 100 atom got trapped here, another 100 atoms got trapped here, and similarly these. And by looking at this false color images, what we try to do now is that, of course, two way. One, we are trying to make sure one single atom will be trapped in each of these sites. Second is that we want to bring the distance between them also closer. And the third is that we want to actually now selectively address one atom here with a different quantum state, so that I can call one as 0, one as 1, one as 0, and this is like a 0, 1, 0, 1 kind of quantum information processing. So this is one thing what we are doing. So these are atoms, these are neutral atoms. Oh, these are absorption image. This is same technique as I explained previously. So what you do is that you create these traps, and then you switch off the trap, and immediately for a very short time, around 10 microsecond, you shine an absorption light beam which falls on the camera. Wherever the atoms are there, they absorb, so you get a darkness. So these are absorption images. Of course, we are also going for fluorescence images. Yes.
Resolution?
So here the resolution is around, I think, less than 5 micron. So the distance between one site to another site, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, around 50 micron. Yeah, but of course.
That one option thought you have how many?
Typically 100 at present, but we are working towards having a single atom at a single site. So that is the direction the lab is going. Yeah.
So the atomic size is much smaller compared to.
Yes. Correct. So now the question is that if you look at the size of an atom, which is like a Bohr radius, which is much smaller, but now in this kind of situations, this will always be diffraction limited. So so that is correct. For example, the numerical aperture of our imaging system now, what we have installed, so that is like 0.55. So this will allow us to stay within a resolution of 0.9 micrometer. So we will always see an atom anywhere between that 0.9 micrometer as one atom, but that's okay for us. We can always, if it is a single atom, then we can always make sure that whether it's there.
How do you kind of make out how many atoms are?
Oh, that is from the darkness of the image. You can actually calculate. Yeah, strength. Yeah. All right. So there is another thing which. Yeah.
So you can also study Rabi oscillations.
Yeah. People have done that. Yeah, that is relatively easy. Yes. Okay. So another thing what we do is that since we have this nice device, we can create what is known as these helical beams or orbital angular momentum carrying beam, OAM, and the idea is that the phase progress as the light propagates is 2 pi across the square. So we can create this using this device, and then we can demonstrate that indeed we have created this orbital angular momentum creating by interfering. You can see this interference pattern from left to right there is a fault, and that actually shows how many topological charges this light have been carrying. So for example, we can create this. Okay, this was a little detour how we create it. But what I wanted to say is that once we actually can create this orbital angular momentum carrying beam, we can either verify using the interference pattern which I showed from the lab, or for example you can interfere with an orbital angular momentum, let's say -1 with +1, and then you can see this fantastic what is known as this petal interference pattern. By counting the total number of interference petals dividing by 2, you know how many topological charges you have created. So one of the activity in the lab is now to shine this orbital angular momentum and spin angular momentum carrying light to interact with these atoms, and this is by definition entangled light because orbital and spin angular momentum are entangled with each other, and then with atomic degree of freedom, so we can create a higher order entanglement as quantum resource. Topological charge, yes. Oh, okay. So, so typically what I mean by topological charge is that imagine a Gaussian light. Now you can make the Gaussian light circularly polarized, let's say right or left circular polarized light. So that is known as SAM or spin angular momentum of light, right? Now you can make sure that the entire Gaussian phase, suppose you take a cross section, so typically that's the same phase, right? That's the definition of the Gaussian beam. But imagine that along the propagation direction, if you have a, for example, if you have a plane cutting that propagation direction and you measure instantaneously the phase at various points, if the phase is, let's say, with respect to some defined phase 0 here, then at 10 degrees something and so on, and then entire rotation, if the phase has progressed by 2 pi in the clockwise direction, you define it as a topological charge 1. You can also create something which rotates by a 4 pi phase shift. This is called a topological charge 2. It's another way of saying, suppose you take a quantum matter and then you rotate, so you will not be able to rotate like a water in a bucket, right? You will create vortices. So there, if you rotate with a phase shift of 2 pi, you will create one vortex. If you rotate, then you will create with 4 pi, you will create two vortices, and so on. So you can eventually make, because this is because the wave function needs to be contained. I mean, it's the same principle as that. So now one thing which is of very much. It's not a not a Coulomb charge, for example. Yeah. So it's another way of saying giving it's a term. Yeah, correct. Yes, it is conservation of angular momentum, but then you can make it. Okay, so if I now have 5 minutes, I don't know. 5 minutes? Okay. So I will quickly tell you something what we had done using these atoms. So we looked at what is called the spin fluctuation of these atoms. It's a relatively modern field. So for us, the meaning of spin is the following, that an atom will have a nuclear spin, then orbital angular momentum, electron spin, all this you have studied probably, and I don't know, liked or hated. But then at the end of the day, after this fine and hyperfine structure, you end up with this total angular momentum state F and its projection, for example, in a particular quantization axis. So for f equal to 1, you will have 3 projection, right? 2f plus 1, -1, 0, plus 1. And for us, the spin means that. It's almost the similar concept of an electron spin, which is spin up or spin down, but for an atom this is a way to do that. For example, a complex atom like rubidium, what I mean is that this corresponding ground states F equal to 1 and 2, in presence of a magnetic field they can have this magnetic spin state. So these are called MF states. Okay. So now these magnetic states, if you have an atom in any of the state, you assume quantum mechanically it will stay in that state forever, right, unless there is a process of decoherence. But suppose there is a process, so the atom can particularly stay in a state MF equal to +1, now after 2 seconds can go to 0, then again come back to 1, go to -1 and so on. So this process can have various origin. There can be thermal reasons for that, there can be quantum fluctuations for that. So at present let's not ask the question what is the cause of that, but the question is that can we measure it? Can we measure if an atom is fluctuating from one state to another state, which according to quantum mechanics is a surprising thing, right? But now, yes, it turns out indeed we can do that. So we look at these quantum spin fluctuations between the different states and how can we measure it. So typically in presence of an external field, an atom in a given spin will do a Larmor precision, and then if it fluctuates into another spin state, so it will now do another Larmor precision, but according to that. But if you know your quantization axis to make a measurement, you will be able to detect it. So that's what we do. So this is another small detour. You all know about Faraday rotation in presence of a collinear magnetic field. That means when you apply a magnetic field, the energy level shifts, and we use this happily every day to, in our lab at least, to do this magnetic laser cooling. But in this case, we actually do something else. We actually now try to look at the, for example, polarization rotation. So we have a beam splitter here, and in these two detector, if suppose there is a non-zero magnetic field, we will see a different polarization vector. And this is, for example, you can nicely see this red one is an absorption from a bunch of cold atom, and then as you change the frequency, you can actually look at the Faraday rotation signal. So this is something which is known. I am not discovering something, but what I will try to explain now. So now there is another concept which is also known a long time back, which is called the fluctuations in any measurement. For example, if you take a resistor, pass a current through it, now there is a, depending on the temperature, this is classical, the voltage across the resistor, its squares mean value, that will be non-zero, that need not be zero, right? According to Ohm's law, this will be just R equal to V by I, but you know, this according to Johnson-Nyquist noise, this term is also non-zero. So now the spin, when I say that there is a, for example, two magnetic state, and the spin is fluctuating, what is zero is the average of the spin projection in one of the direction, but its square need not be zero. Okay. So if you do a correlation measurement of this quantity Sxt and Sx0 and do its correlation term, that is not necessarily zero if there is a any source of fluctuation, be it quantum fluctuation, classical fluctuation, and so on. Now you simply need to measure this quantity and take a Fourier transform, and then that Fourier transform in the frequency space will show up a peaked function. So this kind of measurement in atoms, so this we got started with. First we did in a vapor cell in room temperature, and actually in the vapor cell itself you can now see an excessive noise over the short noise level. Well, when I say excessive, this is still like nanovolt per square root of hertz. This was a big challenge for us nearly for an year to measure. Lots of electronics and technique development we had to do, but then we can measure this. Now once we can measure this, at various magnetic field, and one thing I avoided saying, this magnetic field is always applied to the perpendicular direction. So this is not what is standard known as Faraday geometry, it is known as Voigt geometry. The Voigt geometry allows you to define the quantization axis where only the fluctuation is measured, not the shift of the polarization state, and which actually helps to take us what is known as this background free measurement, and these signals are all background free measurement. So now as you can see, as you change the magnetic field, the position of the noise peak also shift, and so in the reverse direction this is also a magnetometer. And why this is a better magnetometer? Because you want to look at a Faraday rotation itself, that will be marred by even if the laser polarization was also fluctuating. But here whatever be the laser polarization fluctuation, that is simply subtracted out. So it's a common mode. So only we are sensitive to the external magnetic field. And then we did various studies. I don't want to get too much into detail of that. Surprisingly, we also see from the so-called Bright-Treby formula the appearance of the nuclear spin level. So you can, even doing an atomic measurement, can make a measurement of nuclear spin fluctuations as well, which is something I myself was very impressed to see for the first time. So now, we had used this device over the past 2-3 years to make a time resolved magnetometry. For example, these YOLO lines are time resolved measurement in presence of an external magnetic field over a time scale of a few hundred milliseconds, and also spatially resolved magnetic field, because both the line shape and the strength of the signal is dependent on the magnetic field orientation as well. So we call it vector and time resolved magnetometry. And then we developed something thanks to Raman. Before that, we also can measure the fluctuations of the spin state in different hyperfine states in atom. And that is important because many of the time when people do atom interferometry, people actually tries to measure the population of an atom in different hyperfine state, and those measurements are always one shot, because you don't know, so people try to prepare the system again, make a measurement. Here this measurement is totally non-invasive, because we are actually measuring a phase fluctuation of a light interacting with the spins of atoms, and this is not disturbing the spin state population. And by now pumping the atom from one state to another state, we can also see the qualitative nature of the signal. We have explanation for this. So we can actually measure the real-time population in different states. And now the question is that, of course, this experiment we did artificially pumping the atom from one state to another state. But if there are other phenomena, for example, you are doing this measurement here, or if you are doing this measurement where the gravitational field is much weaker, so the two ground state population will be different. And so this is also a aid for such measurements as well. So now after that we can also do what is called a two-photon coherent excitation between the magnetic spin states of this atom, and then we can enhance the so-called spin fluctuations. So this is like a Raman aided or Raman driven spin noise correlation measurement. And those measurements, now you can see that going down from the nanovolt per square root of hertz, we can typically get into the microvolt per square root of hertz kind of range. So this actually increased the sensitivity of the spin noise spectroscopy signal. So then what we could measure, the spin noise in cold atoms is much narrower, and we can use it as a sensor with more precision, typically factor 100. And we can also make sure that the spin decoherence lifetime by just measuring the width of such signal is of the order of a millisecond. So that also gives a long-lived quantum state. So that's all I wanted to say. Please, if you have any questions, ask me. So I'll be very happy.
Getting to the the earlier middle part of the talk, we talked about the trap, right? So you mentioned about the decoherence in milliseconds. What is the source? Is it a CW source or a pulse source?
It's always CW.
CW
Yeah.
source. So like when there is a constant light background,
Oh, okay.
how
okay.
are you measuring?
No, I understand your question. No, see, for example, when you have the atoms in trap, which is also having light present, so then the decoherence time scale is much shorter. That is limited by the excitation, de-excitation dynamics. But the lifetime of a particular quantum state in a dark trap is much longer, of the order of millisecond, because there is practically nothing which stops an atom which is in the ground state to decay into any other state. So what we do is that we first spin polarize these atoms into the absolute ground state of the atomic state, and then the temperature or any thermal agitation is much lower than the corresponding energy difference between any other state the atom can.
So here there is no electronic transition.
No, there is no electronic
So there is-
transition.
so there is
So
no
only
decoherence.
then.
Yeah.
So once you state prepare and leave it, then the lifetime is in milliseconds.
Thank you.
Yeah.
So for want of time, we'll have questions after the session, sir.
Sure.
Thank you so much for your talks. Thank you so much for your insightful talk, sir. Now I'll request Professor K. Srinivasan, sir, to offer a token of gratitude to Dr. Saptarishi Chaudhary, sir, as he had taken time from his busy schedule to come all over from RRI to give us insights on ultra-cold atoms. And thank you so much, sir. The next speaker for the morning session of this lecture series is Dr. Natarajan Kamaraju. Dr. Kamaraju is a proud alumnus of our institute, completing his bachelor's and master's in physics from 1995 through 2000. He did his Ph.D. in the Indian Institute of Science in the topic of ultra-fast response and time-resolved spectroscopy of carbon nanotubes, semiconductors, and rare earth titanites. He's an accomplished associate professor in the Department of Physical Sciences, and he heads the ultra-fast terahertz spectroscopy group at IISER Kolkata. He has garnered extensive expertise in the field of ultra-fast dynamics in condensed matter systems. Throughout his career, Dr. Natarajan has held various significant positions, including postdoctoral research associate roles at institutions like the Los Alamos National Lab and the Rensselaer Polytechnic Institute. His research spans a wide range of topics, from magneto-optical terahertz spectroscopy to coherent phonons, with a focus on exploring quantum effects in low-dimensional condensed matter systems. Dr. Natarajan's contributions to the field are reflected in his numerous peer-reviewed publications and his recognition as an outstanding reviewer by the prestigious Nature Light Science Applications in 2018. He's adept in both experimental and computational techniques, having designed and built sophisticated spectroscopic setups and demonstrating proficiency in various simulation tools. Overall, Sir stands as a distinguished researcher and an educator with a passion for unraveling the intricacies of ultra-fast dynamics in condensed matter systems, making significant contributions to the scientific community. So we are very privileged to have you with us delivering talks. Sir will be delivering a talk on the topic ultra-fast UV visible FIR and terahertz pulses as probe for condensed matter material systems. Without further ado, Please join me in welcoming Dr. Kamaraju Natarajan.
Thanks so much for the nice words, and I thank the Department of Physics, SSSIHL, for inviting me here, and it gives me great pleasure, and and also talk in front of my own teachers. So thanks so much, and I'll just get started. Probably my talk is, I have put it in such a way that it will be at a pedagogical level in the beginning, and then slowly I will shift gears. And hopefully you will also be able to appreciate what I want to tell you at the end of the talk. Okay, so the title is like, I have just kept it, what I've started doing, after I joined IISER Kolkata. So, okay. So IISER Kolkata is the institute which was started in 2006, along with, I think, IISER Pune. And we are located, we have been at various places, but finally now we are in, near somewhere around 50 kilometers from Kolkata. Our campus is about 200 acres land. It's nice greenery all around. And we have few entry points for IISER Kolkata. Is 5-year BSMS course. We have Ph.D, integrated Ph.D, MS by research, and other various, institute postdoc program is also running. And we are about 7 departments. These final two departments, what you see, data science and humanities, are the recent ones. Okay, so I'll come to, so my work hours, right? So this is actually the laser which I use for all my studies. So I use ultra-fast and terahertz spectroscopy as a tool to look at condensed matter systems. And when I say ultra-fast and terahertz, basically it's all optics, basically, right? You use optics to look at condensed matter systems. And light, when you talk about it, having studied here and having gained the background in light, light, and then I went on to do light matter interaction. So the training what I got here was very important for that. And also light I've been always fascinated, right? So because, it gives you an opportunity to look at things, many other things that are happening around. And so that's how I start with. And so when I tell you pulse, pulse is, so you take a torchlight and then, that's the CW, right? I mean, continuously light is coming all the time. Now, if I want to make it as a pulse, then there's something called mode locking. I will not go into the details of that, but so we have these pulses and then we use that to study the system. So if I ask you, what are the fastest events that happen in, around you? So So this is my group. So mainly I'll be talking about the work of Shomya and Anjan. So there are other 3 students who are in their 3rd year. These 2 will be graduating soon. And so, okay. So I also have to tell you what I have, these are some of the interests. Maybe I'll just quickly go through this. The first part is I started with looking at ultra-fast multi-species dynamics, that is many-body dynamics that happen in condensed matter systems through pump probe spectroscopy. And also using spectroscopy to look at condensed matter system, developing some or discovering some new methods to look at the condensed matter. And another direction is to use coherent phonons to study or coherent dynamics of quasi-particles, right? And terahertz we use, in our group to look at the spectroscopy, basically to identify materials, because every material on this earth has, characteristic terahertz absorption. And And in a terahertz spectroscopy, when you want to do, you have to be very sure about the analysis. So for the analysis to be very good, you need to be sure about your thickness of the sample what you're using. So we developed some algorithms, numerical algorithms to do that. And another area is terahertz metamaterial or terahertz photonics, where we use terahertz for doing photonics, right, our metamaterial research. So why is it very important? Because terahertz again has a longer wavelength, so making the samples become easier. So that is another direction I look at. So to outline the talk, mainly I will give a pedagogical, a kind of introduction in the beginning, and then I will go into the research work what I wanted to present. Okay, so fastest event, if you want to think of, it's basically a, right, whatever you can, I just, as an example, I've put this. So this is taken from a National Geographic channel where you see this hummingbird flapping. So the one flap takes about 12.5 millisecond, right? And then our eyes cannot see that because our eyes response time is about 50 to 100 millisecond, and these, flap happens in order of 12 millisecond. Right now, what is the next fastest event that you can think of? There are many such events. So I think Professor Saptarishi was talking about this flash of camera, right? So that is like microsecond, and in that time, light travels about 3 times the football ground diameter, and the transistors switches at 1 nanosecond, right? And molecular motions happen in picosecond time scale. And photosynthesis, for example, conversion between cis and trans form of retinol takes about few femtosecond, right? So, and then we can go on, like there are many such events, right? So to see such fast events, you need some tool. That's where ultra-fast pulse comes into picture, okay? And so physics or materials, what are the different dynamics you see? There are again, as soon as you excite with the pulse, what really happens? Electrons get excited, and then these electrons have excess energy, and then they give off that excess energy to the lattice, and then how these things, whole thing happen, you can actually take snapshots, just like, taking a photograph of what is happening. Like you have a beehive, somebody, throws a stone, and then how these bees are, coming out. So you can take a snapshot if your camera is fast enough. So that's exactly we do, with the ultra-fast pulse. Right, so what is pump probe spectroscopy? That is the main tool I use. So I'll just tell you briefly what is pump probe spectroscopy. So as the name suggests, pump means something very strong. You have an intense pulse, a pulse gets divided into 2 parts. One is called intense pulse, other one is called probe, because probe on its own cannot perturb the system, right? It just reads off what the effect that was created by the pump, okay? So just like taking a snapshot. So the pump basically perturbs the system, and then, probe basically, probes the system. Okay, so that's why the name pump probe. And so how do we do is you go with you basically focus both of them to a sample, right? So let's say you focus down to something like 50 micron diameter. Now pump in that excited part, it's going to excite the electrons, right? And these excited electrons now going to relax. So basically that process will be captured because there is a time dependent refractive index change in that local area. So that you can read off with a probe pulse, through reflectivity or the transmission. So that's exactly you see here, and you see this oscillations what you see here, on the data. This is basically the reflectivity data from MNBI to TE4. So you have this electronic response on top of that. Those beautiful oscillations, they are basically the Raman active phonons, which are seen in the time domain. Okay, and right. So let me just explain you how do we. Just to tell you how we read off the data. Right. So let's take a system scenario where we talk about semiconductor, because most of the time, we do in our lab is on semiconductors. So it can also be, we can also talk about metals, but yeah, here I will restrict myself to semiconductors. Okay, so you see this data, what you see on the left side. So you have this, there is something called time, t picosecond, that is basically the delay between pump pulse and the probe pulse. So as I told you, a pulse comes, gets divided into 2, and one part is going through the motorized stage, where you basically change the arrival time of the pulse at the pump, right? So you, so when I say minus 20 there, whatever it is written, minus 20 picosecond, what that means is that your probe goes first, right? And what you're seeing is delta T, which is a change in the probe transmission because of the presence of pump, okay? So that is going to be 0 because probe on its own is very weak, and if you just shine on something, it will get absorbed, right? And there is no change because of the pump, because pump here, probe goes first. When I say minus 20 picosecond, that means your probe pulse is going first, your pump pulse comes later, right? So probe will not see anything because probe is going first. So you don't see anything, so delta T is 0, and so that's the scenario that is seen here. So you can see probe is going first and pump is coming later, okay? And if I just go a little ahead, when pump and probe are coming at the same time, okay, so another scenario is that, okay, here I have assumed that the photon energy of the pump, yes sir, so that's what I just forgot to tell you. So this is basically the pump and probe photon energy is actually more than the band gap of the material. So basically, when both of them arrive at the same time, pump bleaches the levels and then probe doesn't see anything, so probe transmission suddenly goes up, right? And then with time, like as you simply keep varying the delay, so just to tell you the delay, what we are talking about is in, okay, this is picosecond, but I can go in steps of 3.3, femtosecond, because 1 micron is like 6.6 femtosecond. So because you have to take, going and coming back. So that is like 6.6 femtosecond, I can actually move. But that again depends on the pulse width. If my pulse width is like, let's say 60 femtosecond, there is no point in moving in 3.3 femtosecond or 6.6 femtosecond. Though I can move, but it will not have anything. So basically my pulse, my pulse resolution basically decides what step size I want to move, okay? So this is a situation where you see pump and probe photon energy is more than the semiconductor band gap. And as you see, as you go here, there is a decay of that state, whatever you have excited, and that's how you try to understand what is happening in the system, right? So this is called ground state bleach. From the ground state, things have gone up, the electrons have gone up, and then how the electrons are coming down. That's what we are tracking here, like taking a snapshot, right? So this is another case which is called excited state absorption, which is called you need pump to see some effect of that, in the probe. So probe on its own cannot excite anything. So your photon energy is, pump photon energy is much more than the band gap, okay, but probe has energy, photon energy much less than the band gap. So probe on its own cannot excite anything, right? So you can see here, so it is going negative means it's the pump induced absorption, right? So transmission is going down. So negative doesn't mean, here it means that it's just effect of pump, okay? So your delta T, when you are seeing it, you will see suddenly it goes down and then, it comes back. Okay, so if I have to summarize all the processes that can, this is a very general slide. You can, like, let's say you have a valence band and conduction band of a semiconductor. So what you do, right? You can summarize everything. So you can excite with, let's say, very high photon energy and probe it with white light. White light meaning that it has all the wavelength, right? So you can see here. So this is again, so this is the. Okay, so I should use this. Okay, so this is, so you can see that this is a lambda, and then on the x-axis, so you have ground state bleach, and then you have, you can also track stimulated emission if it is happening in your system, right? And this is the excited state absorption, okay? So this is in a kind of a small walkthrough about the technique what I use. And let me just summarize whatever I've been saying. So it's basically the semiconductor, right? And if I excite, the electrons go from, so it's basic, I have basically instead of a 2D diagram, I've actually put a 3D just to make sure that you understand what I'm saying. So this is, you have both momentum relaxation and the energy relaxation here. Yes, sir, it's a direct band gap, sir. Yes. Just I've taken it a very simple case so that it can be explained. So you see the electrons are going to the excited state, and then you have this intra-band relaxation, right? So first electron goes, as soon as you excite, it goes into the non-Fermi-Dirac state, because you cannot really describe the temperature of the electron. So it takes about few tenths of femtosecond. It comes to a common temperature, electron temperature, and the lattice temperature is different. And then slowly it exchanges energy with the lattice and then loses energy, and then comes to the bottom of the conduction band. And from there it can recombine with mid-gap state or without mid-gap state. So basically we have tried to study this, in a clean semiconductor, or if you make a nanoparticle, you will always have some kind of mid-gap states. Now how that is affecting the relaxation, right? Not only electrons, you can also, this is very simple picture I have given it for electrons, but you can also think about for holes. And we have also done some measurements on, hole dynamics. So right now that time scale is very fast, so we will not be able to see here the electron coherence time if you're talking about, but yeah, but for phonons, yes, phonons we can see that. Yes. Because of the heat capacities are different, right? The electron heat capacity is much different from, right, lattice. So lattice temperature is always slow.
Then what do you mean by non-Fermi-Dirac state, sir?
So how do you describe electrons? So you have to use, because they are fermions, right? So you have to use Fermi-Dirac statistics.
Yes, sir.
So what happens immediately after excitation is that they go into a non-Fermi. So you cannot really, so if you try to look at the density of states, it cannot be described by Fermi-Dirac distribution.
Is it because of the the perturbation, sir?
Yes, strong perturbation.
Oh.
So it is not well understood what really happens. So people have try to model. You can't even model it because you cannot really describe a temperature. So there are like advanced computational tools which they try to decipher something from that. But so basically we can do this simulation. We can try to see how the density of states. Still it becomes a Fermi-Dirac distribution. You cannot really, you will see in simulation also, you will see that it is happening, and then once it reaches a Fermi-Dirac form, then you can associate a temperature. Yeah.
Thank you, sir.
Yeah. Okay, so this is a setup. Sorry. Yeah. So this is a setup. You can see that. Yes.
Sir, how much is the band gap energy for this case?
You said what you were asking?
Band gap energy.
So I said photon and probe photon energy. There are different cases I discussed. So they are more than the band gap or less than the band gap. Are you asking what is a band gap? So this is a general thing I was talking about, right? So the band gap for example, if you take an example, silicon, that's an indirect band gap semiconductor, which is having band gap of 1.1 eV. Indirect band gap, you know what it is. Your gamma point, your valence band and conduction band is somewhat separated from, K point. Right? If you take germanium, it's 0.3 eV, and zinc oxide, I think it's about 3 eV or something. So it depends on what material you are studying. So you choose your photon energy such a way that you can understand what is happening in the system. So you have to, that depends on the system what you are studying. Okay? Yeah. So you see this is the pump pulse. Okay, so the femtosecond laser pulse comes out. You have a beam splitter which splits into two. This is a probe, and this is this side is pump. I have a second harmonic crystal to generate 400 nanometer because I want to excite at little above, so that I can study many materials at the same time. So I choose materials whose band gap is smaller than this 400 nanometer or 390 nanometer in my case. Okay, and this goes and hits the sample, and the probe is basically taken through the motorized delay stage, which actually changes the arrival time of this pulse at the sample. Okay, and then I compare this output, that is the probe which is interacting with the pump, and also the probe that is used as a reference, part of the probe. Okay, so I take the subtraction between the two. Okay, so this is like a femtosecond pulse. As you can see, this is the repetition rate is 100 to 250 kilohertz. 100 kilohertz means it's like every 10 microsecond you have one pulse. Okay, and each pulse you take separate into two, and we do this measurement, and we we sit at the delay and average it over many times. Okay, yes sir. Yes. It can be, sir. You have to choose. I mean, accordingly, we have to look at the system. So, in my system, I wanted to look at the photo-induced absorption. So, I've used higher photon energy and a probe as a low photon energy, so that it doesn't really, look at anything that is happening in the ground state. Yeah. So basically, you look at this delay between, I mean, you just vary the delay at each and every delay. You sit for like thousands of pulses, right? And then take the transmission of this probe pulse as a function of this delay, okay? And that's how you record your data. And so this part is like something I've just summarized in one slide. But because I want to talk about terahertz in a minute. So this is like, we have tried to look at various many body physics. For example, in V205, we have looked at polarons dynamics. And for hematite, we have tried to look at the self-trapped excitons. And whole dynamics has been, investigated in this copper sulfide Ag2S. And COV206, where we see two type of traps. We are able to, differentiate between shallow traps and deep traps. So this I will not go into the details, but yeah, the papers are listed. Maybe at the end of the talk we can also talk about it. You can read through this. Okay, so let me just tell you about terahertz. So terahertz is it's an electromagnetic region which is between microwaves and IR. Okay. If I have to define, so this definition actually keeps changing. Now terahertz community is so, growing so fast. First it was 0.1 terahertz to 3 terahertz. Now it is, I mean, when I was doing postdoc, it was 0.1 to 10 terahertz. Now I think it has even gone slightly higher because we are able to make these sources. So this was called terahertz gap because there were not enough sources or detectors in the nature, right? So even if the terahertz source, terahertz radiation was there, but we were not able to feel it because we didn't have enough, detectors. Right, and there were of course thermal imaging and all was there, but really this scenario got changed after the invention of femtosecond lasers. Okay, so once femtosecond lasers came into scene, we were able to generate terahertz on the tabletop. So we could make terahertz sources and terahertz detectors also. You can detect whatever you are generating, and that opened up a door, for this terahertz technology. So gap has become a technology now, and a lot of research is going around this terahertz spectroscopy because it is again non-invasive and it doesn't really, it's a low in photon energy, so it doesn't harm and things like that. Okay, so the definition is like if you have to look at in MeV, so it is 0.4 MeV to 41 MeV, and that already tells you that you can actually excite the low energy excitations directly. So instead of indirect way, like I was saying you, right? So optically you excite electrons and then these electrons give off energy to the, low energy excitations. Now I can directly study these, low energy excitations like phonons or, excitons and polarons and things like that. Because only thing is that your binding energy of these have to be in the MeV, right? Whatever you are probing. So, yeah, so this is what I was saying. So not only this, I mean, you can also, if you can increase your electric field strength, you can also control these excitations. Okay, that's something I'm interested. So I will probably venture into this regime at some point of time. But yeah, so this is like right now, my laser doesn't allow that to happen. I mean, because my laser energy is very small, I cannot really go with that, megavolt per centimeter kind of electric fields. Yeah. So you can imagine here, so if I have 100 megavolt per centimeter, you can see that magnetic fields, you can actually have a pulse of 33 Tesla. So you can imagine what kind of perturbations you can make to the system and study what's happening. And so terahertz has fingerprint absorption. Every material on Earth has a fingerprint absorption. So which means that's why it is very much useful for identification of chemicals, pharmaceutical industry, and bioimaging, or surveillance, right? Or, like this kind of, if somebody has a very dangerous substance and you just terahertz, you just pass terahertz, it will tell you what material it is, right? So, and this is a recent development. I think Sundaresan is one of the company which has actually developed this. So right now, I don't think we have it in India, but US, some of the airports have this 0.3 terahertz, scanning systems. Okay, and this is about communication. This is from Fraunhofer Institute. I think there are only 2-3 institutes in the world have this kind of capability. Now they are working on 6G. So we will have at some point of time, now we have 5G, but at some point of time 6G when it is coming, most probably we'll have terahertz sources and detectors, for that. Okay, and so this is a summary of what terahertz can do. And so for example here, standard wireless 100 Mbps data of the rate at which data can be transferred can get enhanced to something like 100 gigabits per second, right? So let me just quickly tell you about how terahertz we generate. So I'll just take 2 minutes to tell you so that I can also talk about what I wanted to talk about. So this is an optical rectification process where you shine light onto a nonlinear material, right? And because of different frequency mixing between, so when I say a pulse, you have to appreciate, like if you take a Fourier transform of a pulse in time domain, you get a spectrum, right? So you have many longitudinal modes that are there, and all of them are like there's something called mode locking, because of which your pulse is produced. And these individual, maybe I have those, yeah. So you can see this is your pulse spectrum. These are the individual lines are basically the longitudinal modes, right? And you can have mixing between these modes, and the difference between them is in the terahertz domain, okay? So you can actually create the polarization because of this difference frequency mixing, so dou square P by dou T square. So that gives you the radiation, terahertz radiation. And for that, you have to have the phase matching condition, which is the group refractive index should be equal to the phase refractive index of the terahertz, for generation. So basically, the group velocity of the incoming light pulse should equal the phase velocity of the terahertz pulse that is generated. Okay, so we generate that, and so this is a terahertz generation, and then detection is exactly inverse of that. You use something called Pockels effect, so because these are electric fields. Okay, one more thing. In light, we detect intensity, but here we detect the field strength, electric field strength, right? So that means that any changes that electric field in time domain it is producing, the refractive index, we are talking about changes in 10 power minus 5, refractive index. So those things can actually be detected, because that if the refractive index is getting changed, it is going to change the transmission of the let's say another 800 nanometer pulse that goes through the polarization. If you know what it is going to track how the polarization is getting changed, because whatever small changes what delta n it is getting produced, that will be seen by the terahertz the 800 nanometer pulse. Which one? So here we are talking about just the electric field strength, how it is affecting the refractive index. So this is the setup, like you can see. So light, so this is the NIR light, and then the terahertz. So this red is terahertz. So you have some kind of detection crystal. So if terahertz in time domain, it is basically changing the ellipticity of this material. So it actually rotates the polarization, and then if you have a lambda by 4, which let's say in the absence of terahertz, you'll have a nice circular polarization. You set your lambda by 4 in such a that such a way that you have a nice circular polarization after that, and then you have Valentin prism which splits into X and Y component, and then you look at the difference between these two components in time domain between the pulse, terahertz pulse, and 800 nanometer. Okay, so that's how you so it is directly linearly proportional to the electric field strength. Okay, and okay, so I think now I will shift gears into what I want to tell you. So this is the slide where I was showing you about how terahertz is. So you can see this. So this is a terahertz field, let's say you have in time domain, right? And you basically move this NIR pulse in the time domain, arrival time, by changing it at each and every instant of that time. I wait for, pulses to get averaged, and then I look at the difference between the two photodiode output, which is basically telling you how the electric field is rotated, or how the 800 nanometer intensity or the polarization is getting changed because of the time dependent field strength. Okay, so let me I have some, okay, yeah. So again, as I told you, the group velocity and the phase velocity, they have to match. So there are only few materials which have that. Zinc telluride is one such naturally, in nature it occurs naturally like that, where you have. And there are other systems, I think gallium phosphate, or I'm not very sure. There is one more crystal which also has, you can do it at 532 also. So basically you have to have the phase matching condition correctly. So that is the main thing. And also recently I think there are like a lot of organic crystals which have, phase matching around 1550. So, you can generate terahertz using 1550. And as I was saying, like there are like again some other materials where you can tune like in the lab, where you can detect terahertz in that regime. Okay, so let me just take you through the material first. What we have done some I mean, this is from my lab in the recent measurements from one of the student, Shomu Mukherjee. So what are topological insulators? So they are like, you have a so normal semiconductor, right? But here this is actually shown here. You can see this. So in the bulk it is semiconducting, okay, but on the top it is conducting. So you have the surface states which are actually given here. Yeah, these are surface states which are there, right? And so which are conducting like graphene. And then you also have the bulk. You can see this nice valence band. Sorry, this is valence band, this conduction band. So you have a band gap. So this band gap in this material, these are like bismuth telluride, bismuth selenide kind of material, because it's similar family. Okay, so 0.3 eV is the band gap of the bulk, and your surface states, you have this Dirac point. This is a Dirac point, you call it, right? So a lot of interest has been there for the last 10-15 years. Now why we were interested in magnetic topological insulators is that by doping with in a topological insulator material, you can actually break the time reversal symmetry. And sorry.
So the next slide, sir. The next slide.
Yeah.
I think that you mentioned surface and
yes, it is in the momentum space.
Yes,
correct.
Yes. Whereas I think the next figure C and D, in the same picture, I think they are talking about the physical surface, real space.
Yeah, right.
How are they related, sir?
So that is in the Fourier domain, right? So this is basically in the Fourier domain.
Yes.
When you go into the Fourier domain, how the so this is in first Brillouin zone, right? Whatever you are seeing in the first Brillouin zone, and this is the physical image. So they are already related. No, so there is a correspondence between the Fourier space and the real space, right? And whatever we are saying about the conducting surface, that if you look at it in the momentum space, that's like a surface state.
Right? Are the surface just always characterized like Dirac cones, sir?
Yes, yes. So I mean, why they are called topological, right? So there is also something, if you take a cup and a donut, that is some very famous, you will look at, in YouTube, there are nice lectures on that. So you deform it continuously, then you go into a cup or a donut, right?
Yes.
So something similar, but here we are talking about the band structure. So here, there you have something called hole, number of holes in your surface, right? So here we are talking about, so let's say here, this is a Fermi surface, let's say this is a Fermi surface, this is a Dirac point, right? So how many times the bands are crossing, so that is like, that gives you something called churn number, and you try to understand what, so that's how there is a correspondence between the topological in the geometry, and it's in the, we call it topological insulator because of that topological connection.
One related question, sir. Generally, DFT is used for calculating the bulk band structure. What codes or what theories is used to predict the topological band structure?
Okay, so that's something I think you can use a tight binding model and also DFT, but I'm not very sure. So this is a tight binding model. I know it can be used. I think DFT also should be. Yeah. So, but anyway, so this is no longer theory now. You know, people have seen it in ARPIS.
Yes.
So it is very nicely fitting to a data. I mean, DFT is just to support, but people are able to see it in real time, how the momentums, in the momentum space, how things are happening.
Thank you,
Right?
sir.
Okay. Okay, so, so I think let me come back to this. So why are we interested in this? Because this magnetic topological insulators, you have the ability to observe quantum anomalous Hall effect. Okay, so you know what is Hall effect? So Hall effect is, you know, you apply a magnetic field, you see the voltage generated, right, in the, because of the Lorentz force, that's Hall effect. But now what is quantum Hall effect? You have a quantum, you know, you go into 2D, right, and then you see how the 2D electrons are, you know, responding. So you have this Landau level quantization and all that, you know, why, you know, quantum Hall effect happens. Like if you look at the quantum resist or the RXX and RYY, which is basically if you have a, I don't know, like if you have a, you know, sample where you can look at, so let's say I have, if I have a sample like this and I apply direction and measure the current. You have this, let's say I can measure in this direction, it's called rho XX, and if I try to measure this perpendicular direction, it's called rho YY, resistance in, so you can actually measure rho XX and rho YY, right? And that gives you some kind of plateau kind of thing when you plot it as a function of temperature, right? You have this plateau kind of quantization, no? This is coming because of the quantization in the Landau levels, right? So that, so what we are talking about here is that quantum anomalous Hall effect, which means that even if, without applying magnetic field, you can generate these fields because of the internal magnetization in the system, right? So, so that's where like lot of interest is there in this material, and one disadvantage with this is that you have, sorry, so I think I will. So, so this quantum anomalous Hall effect has been observed at a very, very low temperature in millikelvin, right? Which is not useful, no? So you want to have some material which will be useful for you. So that is where this magnetic topological insulator comes into picture, where people are predicting that you will be able to go to higher temperatures. Okay, so though in reality people have only gone up to 2 Kelvin. Okay, still it is too low, but hope is that at some point of time we'll go to higher temperatures. So we took this material, and so there are again, how to make this magnetic topological insulator. There are two very well known routes. One is that you can magnetically dope, or you can actually grow some magnetic layer on top of the topological layers, which is called proximity effect. So through that you can basically break the time reversal symmetry. So I should also have told you this. So what happens when you have this magnetic doping, or you know, when you have a proximity effect where you have a ferromagnetic material grown on top of a topological insulator, you can actually break this this, you know, surface states into a kind of gap like this. Okay, and that is what is very useful for this magnetic topological insulator, and where the Fermi level is located, that is very crucial for having a high temperature anomalous Hall effect to be observed. Okay, and so the magnetic the magnetic doping is actually very inefficient because it leaves you, you know, some kind of inhomogeneity of doping, because of which you are, you know, you don't really observe quantum anomalous Hall effect efficiently. So that is where we come with this intrinsic topological insulator. You can see this. So how do we make it? We have this manganese tellurium bilayer, which are introduced in bismuth telluride. Okay, so bismuth telluride is a layered material again. So you can see these atoms, right? So you can count the number of atoms, 1, 2, like you have like about 7 atoms. So that's like a septuple. We call it septuple. And within that layer, you have this manganese sitting here, and you have this. So these are spins, okay? So spin direction, and within one layer, you have all the spins arranged in one direction. But if you take next two layers, neighboring layers, they are antiferromagnetically coupled. Okay, so there have been again a lot of contradicting reports of whether this surface states get opened or not. So that's where we wanted to also look at this from terahertz point of view. So let me go over to this. So the Neal temperature is 25 Kelvin. So this again, okay, so this material is, as I told you, it's a magnetic topological insulator. It's a layered material, means you have many layers, right? And they are coupled or they are bonded through van der Waals attraction. Okay, and the Neal temperature is 25 Kelvin, meaning that if I go below 25 Kelvin, this material acts as an antiferromagnet, and above 25 Kelvin it becomes a paramagnet. Okay, and most of the time when you make MnB2, though this material is the new class of material, in last I think 5-6 years this has caught a lot of attention, but you don't have control over where the Fermi level is. So by by way of making your sample, you don't have a control. So the Fermi level always goes and sits in the conduction band, making it always metallic. So that means your bulk and the surface states both are metallic, right? So one solution is that you dope it with some lighter atom, and then that way you can play with your the Fermi level so that you can get to the in the band gap. Okay, and so yeah, so as I told you, like there are RPS and IR studies which have like contradicting views on this, and the next picture will basically summarize what I was telling you. So this is like a cartoon picture of a 3-layer of MnBa2Te4, where below Tn you can see all of them are antiferromagnetically aligned, and above Tn you have like random spin orientation, and so you can see the Fermi level is somewhere here, which means that it is always metallic, right? How? It's self-flux method. So I mean, there are single crystals, but here in this we are using PLD grown sample. Yeah, this is thin films. Okay. Sorry. So how smooth, right? That's what you're asking. So that is like a few nanometers, 1 or 2 nanometers precision. Yeah. So I'll show you. I think I have some slides on that. Somebody asked.
Sir, as you said, the time reversal symmetry will break. So what will be the behavior of electric field and magnetic field at that time?
Sorry.
Sir, you said that time reversal symmetry will change. So what will be the behavior of electric and magnetic field at that time?
You meant, I have not applied any magnetic field here.
Electric field. So what will be the behavior of that electric field?
Which electric field you're talking about?
Like
you mean light electric field?
Yeah.
We are not addressing that here. So it's so once it is broken, see, time reversal symmetry is that the in the surface states are protected. Means whatever impurity you have, the electrons will always be having the same mobility, or they will always be there conducting on the surface. Now once you break the symmetry, time reversal symmetry, you are not protected from the impurities. So it's basically you no longer have a conducting surface states on top. Okay. So okay, so this part I would probably so this is something you have bulk state and the surface states, and then if you play with your SB doping, you can actually have this bulk surface wave function, bulk phonon wave function, right? How it can interfere or how it goes deep into the surface states can start talking to the phonons. Okay, so that is what if you keep playing with that, you will be able to see, and that gives rise to some kind of Fano line shape. Okay, that I will tell you, maybe I will not go into the details of this, but I will tell you in the data. So these are like the lot of papers which, you know, in the recent times on this material. And so this is grown by PLD, okay? And PLD means pulse laser deposition. Again, I will not go into the details, but I will just tell you that you have a excimer laser which goes and evaporates the target, and then, you know, they start making forming the thin film on your substrate. So you can see this, right? The laser comes, yes.
What is the doping levels you're talking of?
Sorry?
What are the doping levels you're talking of?
So I think it's about 0.3. We have put SB of 0.3, yeah. 0.3 or 0.15, I think, 0.15, yeah. Okay, so this is in collaboration with Professor Chiranjeev Mitra, who is an expert on PLD. So he has a PLD setup and where we grow the samples. So of course, these are domains. These are not like a nice single crystals. Yeah, you can see this picture here, a SEM picture. Okay, and so our thickness is about 152 to, you know, one of the sample is 152 nanometer, the other one is 142 nanometer. Okay, and so this is the 4 probe I was talking about. Like, you know, you try to measure the resistance as a function of temperature, and you can see for MBT sample, this is blue, okay, whatever is seen here. You can see the resistance is going down with temperature, which is basically a metallic behavior, right? And below around here, there is some kind of upturn, which is because of some still, I mean, the surface states are always there. You just that I was telling you the Fermi level is like on top, right? So you start seeing some, so you have both bulk and surface effect here, but when you dope it, you immediately see non-metallic behavior. For a pure semiconductor, the resistance should have gone down. You know why? Because, you know, if it is a semiconductor, if you keep increasing the temperature, the electrons go into the conduction band, and then, right, the resistivity should go down. So, and this is for this suggests that you have some kind of mixed state in the system. And now this is all transport, but let's look at what happens. So, okay, so Raman analysis also has been done, as you were asking. So these are some unintentional, you know, defects which also, I mean, you don't have a pure sample. So what I'm saying is that you have like MnBa2 Te4 and MnBa4 Te7. So these are two phases which are coexisting in the system, and but it doesn't really, we still are able to see the signature, but I'm just telling you that this kind of things are possible.
So in a previous slide, around, can you go back to the previous slide? Yeah, so around 200 or around 180, yeah? Little around 200.
Yeah, you mean this, right? Yeah. So this is something we don't understand right now, what exactly that is causing, whether it is, so this is something we have to look at it carefully. I don't think, because there is nothing happening in the system around 180. So I have to see whether, because this is measured by, not by my students, it's from Chiranjeev's group. So I mean, we are trying to repeat this measurement again. So in another place, we just want to check this. But yeah, except for that small thing, others we are able to explain that. Okay. Okay. So now coming to, so we have studied this through Raman, characterized them and all that. And now this is IR. So why IR is important? Because we are doing in terahertz. So terahertz is in the IR regime, right? So you have this particular phonon, 1.57 terahertz, is active in this particular energy range. Okay, that basically involves a movement of manganese atoms. Here you can see this. This is the first mode we are talking about. I'm talking about this 1.57 is actually a EU mode. Okay, it's IR active mode. So with that, let me go into the terahertz. So this is the terahertz electric field, what is measured, right? And in MBT sample and MnBI, so basically SB doped MBT sample, okay? And so you measure the electric field in the sample, and so the samples are grown on a sapphire substrate. So on the sapphire substrate and the sample on sapphire, so both of them you take. And so that's the reference, right? This is a reference sapphire, and then you have MBT, and then you have this or SB doped MBT, right? And this is the electric field, how it looks like if I, you know. So we are generating about like 0.5 terahertz to all the way up to 2 terahertz. Okay, and this is the transmission. So you can see from the transmission itself by looking at it. So there is some kind of dip that should be because of some absorption, right? Just like you have this phonons in this range. So we associate this to a IR phonon. And top of that, when you dope it with SB, you see this extra dips which are coming because of the this anti-side defects. Okay, so
What is the sample thickness?
150 nanometer.
And then your these are like sapphire lattice matched?
Yes, yeah. So, so because again, it's because 150 nanometer. So and terahertz wavelengths are of the 300 micron. Okay, so which means you can always consider that as a thin film, and then we are able to extract. This is called Tin-Cam formula, which probably many of you would have learnt in group theory. Tin-Cam's, so same Tin-Cam who has actually given this nice, which is in the literature we use that. So directly you don't have to really go through. Yeah, thanks. So it has been already worked out. So we use that to extract the conductivity. So this is how the conductivity looks as a function of temperature. Okay, so you can see that conductivity is like here it is about 7 into 10 power 4, and here at lowest temperature it is about like almost twice, more than twice, the conductivity is increasing, right? So that's because at the lowest temperature, you have a much better signal, right? And at high temperatures you have other defacing effects, and that's why you don't see that. Okay, so with that, so by looking at this, you can already guess again. So this shape is like, if you fit to a Laurentian shape or Fano shape. I'll tell you what is Fano. Fano is basically the interference between the phonons and the surface electrons. Okay, so we try to see what is happening. Okay, so I will not go into the details of this. I'll just tell you that this I don't want to. Okay, so this these equations, basically this is a Drude part, because when you excite, the free electrons are there. There is a Drude part, and on top of that there is a phonon part which is called Fano part. I was saying why Fano, I will tell you in a minute. And then you have this extra modes what are seen, right? They are all phonon modes. So basically second and third term is for fitting the phonon part, and the first part is for the free electrons which are there. So this is the fit. You can see this is the data, and the fit is also there at different temperatures. Okay, and I think I will. Okay. So if you see this data, so this is the background you have. This is like this background from here to here. It is actually going down, right? So that's basically the Drude part. Drude, as Drude weight should go down with frequency. So that is basically the Drude term. Okay, so if you do that, and we can also take the spectral area below 0.8 terahertz, and then that actually tells you that there is some kind of things happening around 25 Kelvin. You can see this, though it is very small in MBT, but in MBST it is like a lot of changes. That's because, so what happens is, so let's take this one. As I told you that in this system, right, this is more like a metallic behavior, right, because it's like conductivity. You can think of it like a conductivity. So as you lower the temperature, conductivity is increased, some kind of conductivity is increasing, and then below that, now what happens is, because this surface states got opened, so the conductivity is going to go down. So that's why you see this kind of behavior. So this is exactly what is happening in transport. We are able to track it in the terahertz, and here the changes are very small. Okay, so then we went ahead and tried to look at the other parameters. So Drude frequency is like more like good measure of what is happening. So you can see the changes around that temperature is again like very small for MBT, and this for this it is like much higher. Why? Because once the band gap gets opened, there is Dirac fermions. The electrons have now, because of this band, it acquires more mass, and then because of that, right, the Drude frequency basically, right, gets reduced, because you see this mass. So Ne squared by epsilon naught m star, condensed matter physics, when you are looking at Drude model, right? So this Drude frequency is basically inversely proportional to m, and as m goes down, right, m goes up, this frequency goes down, right? And then you can also see this is a scattering time again, here you have like once you have more carrier densities, the Drude, it basically becomes a phenomenological model. No longer it just tracks only the phonon interaction. It also tracks your electron-electron interaction. So you can see, so your time scales are of order of 60 femtosecond, and there is some small change we are seeing. Okay. So again, this is like it could be overestimation, because our pulse width is like terahertz pulse width is like in 400 femtosecond, but then here we are talking about the Drude scattering, right? So it's like kind of overestimated or underestimation it could be, right? So but still there is a trend which you can see across TN. Okay, and then this is the Fano frequency, that's the phonon frequency. You all know phonon frequency should go as omega is equal to root of k by m, right, where k is the spring constant. So what happens when you lower the temperature? The spring constant is supposed to be increased, right? I mean, it is getting stiffened. So that means that your phonon frequency should go like this, something like this. At this plot, it will be like this. So phonon frequency is supposed to go like that, but you see the exactly opposite behavior here. So this is called anomalous behavior, which had been seen in the literature, but nobody was like has given the clear explanation for it. So we try to understand this for this material. So mainly it has been seen in topological insulator also. It's not that only in magnetic topological insulator it has been seen. So that's why we try to address this point. And so we see that for MBT it is lower, the frequencies are lower, right? For MBST it is actually much higher, right? The frequency, the softening is also more. So if I take the difference between this point and this point, it is about 0.1 terahertz for MBT, and for lowest temperature and the highest temperature for MBST it is 0.2 terahertz. Okay, so that so we try to understand what it is, and I will not go into the details, but if you work out, we were able to address this thing to be like so you have like there are many parameters which affect the frequency of the phonon. And we think it is because of the anormonicity, phonon getting decayed into two phonons, but with a positive, coefficient. So that is what is affecting the MBT. And top of that, in MBST, we think it is because of the electron-phonon coupling. Okay, the electrons talking to the surface electrons talking to the phonons. Why? Because we could fit for MBST to a Fano. So it's like how electron-phonon coupling is effectively happening, that can be looked at by looking at the parameter called Q for this thing here, 1 by Q. So this is well established in the literature. So we use that model to look at this, and you can see this 1 by Q is almost 0 for MBT, meaning that there is no need for Fano kind of interference to be taken care for the MBT sample, for MBST sample, right? So you see a huge change across temperature. Okay, so that's what we have tried to address in this work. And so this is a pump probe data on the similar material. We have done that, you can see these nice oscillations, and as a function of temperature we have done that, and then you can get from the time domain fit, you're getting the frequency and the gamma phonon, which is basically the dephasing time. Why is it important in time domain? Because in Raman you will be limited by the instrument response, where here you are seeing it in picosecond. You can as many times the as much as your phonons are coherent, you will be able to track them. So that it gives you much more accurately, and by fitting two different models, you can understand how much is a disorder in the system. And you can also see here, this is a gamma naught, which is measure of disorder, which is actually more for MBST. So it is actually aligning well with what we were seeing in the terahertz work. And this is something ongoing work where we've tried to look at also how these phonons are changing in time domain, right? So you can do just like a Fourier transform, you can do wavelet transform of the oscillations, right? And then you can see how the frequency is getting, for example, this 2 terahertz mode, how it is starting, and then it is actually frequency is changing and coming to around this frequency, right? And you can also see the another frequency which is getting developed, and this frequency is there only up to 10 picosecond, and the other one is there all the way up to 40 picosecond or so, right? And so that we have done as a function of temperature, and you can see as you go to the lower temperature, for MBST sample there is also another mode which is not IR active, but it becomes IR active. So basically because of some disorder in your system, this can happen, or it could be a EG mode which is there in the system, right? Which is a Raman active mode which can turn into a IR active, if the sample is having some kind of defects. Okay, so I hope, basically, I don't know, the last part probably I was a little going over, but a little faster. I hope I was able to convince you that how terahertz can be used to look at the material property of a magnetic topological insulator. And yeah, and we have found that there is the extra electron-phonon interaction which is happening in the MBST sample compared to the MBT sample. And that I think is a new thing we have looked at. And yeah, so another one work which I'll just quickly, so this is a recently we have put it in archive, where we have tried to look at the strain pulses to track magnetic crossover. Basically CRS-83 is again a layered material. What happens is here you can see this nice picture where your pump pulse goes and produces a kind of perturbation, because these are layered materials. So you are, there is a kind of acoustic phonons, pulse. It's not a single phonon, but it's a pulse made up of phonons. So that actually gets excited, and then we try to track how this phonons pulse, this acoustic phonon pulse, how it is changing with temperature. And we have given a very nice phenomenological theory which actually explains everything, whatever we are observing, taking into account of magnetic interactions, how the magnetic interactions couple to the linear, quadratic and gradient components of the lattice distortions like the phonons. Okay, and so this picture summarizes the result. So you can see this is the Curie temperature for this material, 33 Kelvin, and we see there is electronic background on this material which also shows some kind of changeover around that temperature. And then this is a strain pulse, actually the actual strain pulse what we have observed. You can see below TC, this is how it is, and this is above like room temperature. You can see this is just got inverted, right? So and there are many things. This is a raw data as it is. It also shows a signature around TC, and this is how the phonon frequency changes with temperature, and that has been already we, as I told you, the phenomenological model could explain everything. Okay, and I would like to thank Chiranjeev for the samples, and ICER Kolkata and DST for funding. And these are this is a group, my group. Okay, and below are my collaborators, and I'll be happy to take questions.
I'm just trying to understand what's going on. So because of your terahertz and this lower frequency and electric field you can track, so all your results you do it in the time domain.
Yes.
Instead of the usual spectroscopy where you're doing in the frequency domain. That's the big funda that I can
Yes.
So you are able to see the phonon vibrations and those things in time.
Yes.
By looking at the...
Right. So in the beginning, in the terahertz, yeah, we see it in the time domain.
Time domain in the sense that you're tracking the electric field of the terahertz.
Yes. Yeah, but towards the end, what I was talking, it's not about terahertz, it's about pump probe again. There it is different. So I create strain pulses and then use that to track what is happening in the material. Yeah. So, but as you said, that's right. So terahertz field, because we are measuring in the time domain, one can do also wavelet analysis on that. Like let's say I have another pulse and then excite the phonons. I did not show you the time resolved terahertz, but we also do that. That is, you excite the material with the optical pulse or any other pulse, for example. It could also be another terahertz pulse, and then track how these phonons are coming back. One nice example could be, let's say you take a semiconductor where your exciton binding energy is of the order of, let's say, 7 MeV, which is like about 1.8 terahertz or something like that. 4 MeV is 1 terahertz. So now I can excite the material, right? And then, so excitons would get dissociated. So in the beginning, I will not see a peak at a dip at 1.8 terahertz, but with time, how the excitons are, getting formed, I can actually track that. So just similar to that, I can also perturb the phonons and see how things are changing, like surface states again. So when I disturb them, the Fano shape, what I was trying to understand, the interference between the electrons and the phonons, that could also get changed, and then I can understand how things are evolving over time. Yeah. Sorry, I think I probably rushed over that part. Yeah.
Sir, your last work, sir, where it showed the Lagrangian. Can you just go to the slides?
Yes. Yes.
Yes, sir, what are those terms, sir, if you can, especially the S and Q operators?
Yeah. So these are spins, right? So you have, so how do you model? So you write down the Hamiltonian, no? So Hamiltonian, yes, and then get to the Lagrangian.
Yes.
Right? And so you have this Q square, right? Which are basically the phonon oscillations. Q is actually phonon, S is the spin. How are they? If you have a system, right, what we asked, we just wrote down a very simple picture where you have phonons, right, which are basically the vibration, lattice vibration. What are spins? What are magnons? They are also some kind of spin oscillation, right? This is like a collective mode, right? Now, when both of them are excited, then there could be some talking between them, right? So our strain pulses are getting affected by the spin excitation. That is like when you go below 33 Kelvin. So I did not really talk about this. So there are like very nice regime here. So maybe I have that here. Yeah. So if you see, so this one, so you have something called 2D. Okay. So you can see this picture. Yeah. You see here. So above 110 Kelvin, okay, in this material, the spins are randomly oriented. And as you cool down, there's something called 2D ordering sets in. That's a short range order, right? That starts setting in below 110 Kelvin. Then what happens is, like you can see here. So slowly, short range they are aligned, and then as you lower the temperature, then slowly, all the planes get aligned in one direction, right? As you step for further cool down, that is like 50 Kelvin. This is what. So I call this temperature 110 Kelvin as the 2D transition temperature, because there the short range starts kicking in, and then slowly as you lower the temperature, you go to 50 Kelvin, then slowly, the spins talk to each other, like, between layers, and they all behave like a collective thing. Then you start having like below TC, you have like complete, changeover, like all of them are aligned in one direction. So these are all without applying magnetic field. Okay, so we are able to see that microscopically. This is just like a specific heat capacity, if you measure it for a magnetic system, it will also show something similar to that around, 33 Kelvin, right?
Yes.
Curie temperature. So here we are seeing the same thing, but same transition kind of thing. Like basically all the crossover we were able to track with the phase of the strain pulses. That is the new thing about this. At least I think this is the first time we have used strain pulses generated from material to track different transitions. So we are now seeing it in many other materials also. So and also piezoelectric materials, and also superconductivity is another area we want to use this technique to look at. So yeah.
Basically this Lagrangian is representing the coupling between magnons and phonons.
Exactly. Yes. We have taken a simplest case where you can if you want me to go over that, it is. So you have this, right? So how the magnetic interactions couple to linear term. Linear term is like, this Q, just Q, and quadratic is Q square, and then gradient term is also there. This is a gradient term, right? So, and then you have, so all combinations we have taken and try to model the system. And that could explain how this if you see this, maybe I just ran over this. So if you see this, you see there are two phonons. Like basically, if you take the Fourier transform of the strain pulse, you have this two peaks. One is here. I don't know if you can see this. This doesn't change much with temperature. Okay, as you lower, but this one, is slightly, it's called blue shift, right? I mean, this is like a normal behavior. That's what I was saying. The frequency should go down with temperature. That's what happens here, right? But you see, after 50 Kelvin, suddenly there is a red shift that is happening, and this mode is almost gone, right? Okay, can you see that is gone? Like
yes.
this behavior we could explain. We were able to understand that this is actually, so if you take acoustic mode, there are only 3 modes, right? Transverse acoustic, 2 transverse acoustic, 1 longitudinal. So we believe this is a longitudinal mode, this higher frequency one, or it could be, basically we are saying that these 2 phonons have to come from 2 different branches. It's just not from one branch, and we were able to track down. Just like condensed matter first course you would have studied, how acoustic phonons are,
Yes.
like for a system where you have only 3 modes, right? So basically we were able to track down that.
Thank you, sir.
Yeah.
So for brevity of time, we'll
No, I know.
after.
The time is already, I don't know, what is it? Oh my God.
Thank you
Please
so much.
excuse me for this. I know it, yeah, because I started little late, so probably, yeah. Okay, thank you.
Thank you so much, sir, for giving us insights onto terahertz spectroscopy and the process inspiring us. I'd like to request Professor K. Srinivasan, sir, to hand over Dr. Kamaraju, sir, a token of gratitude for taking his time off of his busy schedule to give insights onto terahertz spectroscopy and, again, inspire us in the process. So we will now break for lunch, and we will meet at 2:30 p.m. Thank you. Sairam.